안녕하십니까. 저는 오늘
Greetings
서울에
everyone.
맡은
I am your MC for
한국국제기술센터의
today. My name
우한연구원입니다.
is Uami
먼저
from Green
바쁘신
Technology
와중에 좀
Center of
시간을
Korea.
내어
First,
오늘
I want to
한미
thank
기후기술
all
혁신
the
포럼 수요 R&D
participants
협력에 참석해
and
주신
our
한국과 미국 양국의
experts from Korea and the
감사
US for
인사드립니다.
attending today's
오늘
Korea-US
진행되는
Technology
포럼은
Innovation Forum on
한국의
Climate Change.
과학기술정보통신기술
Today's forum is
기지하고
hosted by the Ministry of
한국연구원재단과
Science and ICT of
롯데기술센터가
Korea
주관하여
and
기후기술을
co-organized
연구하는
by
국내 정부
NF,
출연연구소 및
NSF and GTC.
과학기술특성화대학원의
And
연구전략을
we have
비롯해
invited
미국 R&D
researchers from
협력연구기관의
government-funded research
연구진들까지 모시고
institutes of
개최하게
Korea
되었습니다.
and abroad.
특히 오늘의
For
포럼을
today's
위해서
forum, we
한국어와
have the
영어,
simultaneous
동시 통역이
interpretation
제공되고
service
있습니다.
being provided in
줌으로
Korean
함께
and
하고 계신
English.
참석자
Those of you
여러분들께서는
joining us on the
필요한
Zoom,
언어를 선택하시면 됩니다.
please select
또한
your
본포럼은
language.
유튜브로
Also,
청취하게
for
되실
today's forum,
경우
we are
많은
being
시청
aired on
부탁드립니다.
YouTube. I want to ask
오늘의
for
연사는
your
오늘의 포럼은
interest in
세션으로
our
구성되어
forum.
있습니다.
We have
첫
two
번째
sessions
세션
for today's
1에서는
forum.
두
For
분의
the
연구를
first session, we
모시고
have
한미
two
양국 간의
speakers,
수소 R&D
and we'll
연계
be
전략에
talking
대해서
about
들어보도록
policies and
하겠습니다.
strategies of the two
다음 세션
countries.
2에서는
In the session
한국 양국
2, we
간의
will have
연구전문가들을
researchers
모시고
of
최근에
Korea and the US
진행되고
to
있는 수소
listen to
R&D
the
연구에
recent
대해서 들어보실
hydrogen
시간을 갖도록
R&D
하겠습니다.
activities.
발표를 다
After
마친
all
이후에는
their
폐관
presentations, we
토론을
will have
통해서
the panel
한국
discussion
양국의 신원책을 낼
to
수 있는 수소
discuss
R&D 관련 협력
various
기회도
ideas to
다양한
generate
의견을
the
청취하는 자리로
cooperation
오늘 행사가
in the hydrogen
구성되었습니다.
R&D field.
본격적으로
Before I go
포럼이
into
시작되기에
the
앞서 녹색기술센터의
agenda, first I want to
이사회장님께서
invite the
저희
president
자리에
of Green
환영사를
Technology
해주시도록
Center of Korea
하겠습니다.
to
다만
open the
이사회장님께서 오늘
session.
갑작스러운
However, due
일정으로
to an
함께 계시지
urgent
못하신 이유가
schedule, the
개회사와
president couldn't be here in
설명사를
person,
사전
but he
녹화해서
has sent us a
보내주셨습니다.
pre-recorded
많은 양해
video of
부탁드립니다.
the welcoming speech. Please, I want to ask for your
Good
understanding.
morning, ladies and gentlemen. I am Sang-Hyuk Lee, the President of the Green Technology Center of Korea. It is a great pleasure for me to hold the Korea-US Technology Innovation Forum on climate change with great interest and support. First of all, I'm very sorry to meet everyone by the screen. This international online forum is hosted by the Korea Ministry of Science and ICT and co-organized by the National Research Foundation of Korea and the Green Technology Center of Korea. It aims at promoting climate technology cooperation among researchers from Korea and the US working on climate technologies. First of all, I would like to extend my deepest gratitude to officials from the Ministry of Science and ICT, the NRF and the NSF of the US for taking time despite their busy schedules. Also, I would like to thank Tae-hyun Yang, Vice President of the Korea Institute for Energy Research, who will deliver a keynote speech, and all distinguished guests who are making today's forum more meaningful. Especially my special thanks to speakers from the US who accepted our request to present online, even though this forum is held at late night because of the time gap. The Green Technology Center of Korea, a government-funded research institute and the co-organizer of this forum, has supported NDE, National Designated Entity, working as a window for climate technology cooperation. In particular, it is actively supporting to create the international cooperation ecosystem on climate technology, since it was designated as a National Climate Technology Cooperation Center this year. Today's forum was designated to bring researchers from Korea and the US together and to provide a space for in-depth discussions on climate technologies innovation and cooperation for achieving carbon neutral. In preparations, the GTC conducted a survey on what field need climate technology cooperation for domestic researchers in advance. Based on the survey results, the MSIT and the GTC decided to hold a forum focusing on hydrogen R&D, on which domestic researchers showed a high demand and interest in cooperation with the US. The US is also making lots of R&D investment and efforts to realize a hydrogen society. Moreover, the GTC would also like to continue holding the bilateral cooperative forum on the various climate technology in the future. As you know well, lots of nations have been pushing for the economic stimulus and the national sustainable development initiative in order to overcome climate crisis and minimizing the economic fallout during the combination of climate changes and global pandemic. The Biden administration has decided to recover the U.S. Paris Agreement to hold the climate summit. Also, it has proclaimed its willingness to recover global climate leadership and promote international cooperation while announcing its high carbon neutrality target. And it is organizing the National Climate Task Force and planning a hydrogen and CCUS program to prepare for a hydrogen society. The Republic of Korea has announced 2050 carbon neutrality implementation strategy and established future strategy of hydrogen technology in effort to promote energy transition and implement carbon neutrality. The hydrogen has been selected as one of key technology considering the national determined contribution (NDC) and industrial relevance. Under the circumstances, I expected that multiple and practical international cooperative research projects are imperative in order to establish an ecosystem spanning from the production, storage, transportation, and application of green hydrogen. In this regard, I hope we could provide a space for climate technology cooperation among Korea and US researchers. Lastly, I would like to ask all participants for showing great interest and support while having in-depth discussion on technological solution to climate crisis. I expect this year's forum could become the beginning of the regular climate technology cooperation forum, which would be held based on the bilateral cooperation between Korea and the US. Once again, thank you very much everyone and online participants.
Thank you very much for your welcoming remarks. As he mentioned, the whole world is faced with serious climate issues. This will be a good opportunity for us to discuss solutions, and through cooperation, we could respond to the efforts to achieve carbon neutrality as well. Thank you very much again for your welcoming remarks. Next, we are going to begin session 1. In session 1, we're going to listen to the presentations about Korea and the US hydrogen-related policies and strategies. First of all, we're going to listen to the presentation from Korea. Mr. Yang Tae-yeon, the Vice President of Korea Institute of Energy Research, will
안녕하세요.
give us the speech.
한국에너지기술연구원의 양태현입니다.
Good morning, ladies and gentlemen. I am Yang Tae-yeon from Korea Institute of Energy Research. Today, I would like to talk about Korea's hydrogen R&D strategy.
본수소 전략은 정부의
Our R&D strategy
산업통상자원부
was formed by the Ministry of Science and ICT, the Ministry of Land, Infrastructure and Transport, and many other public institutions. This is the content of my presentation.
네. 수소 전략을 수립한 계획을
First, I will briefly explain about the background of our hydrogen strategy. As Mr. Lee Sang-yeop mentioned, by 2050, we have to achieve carbon neutrality. This is an obligation of almost all countries of the world.
탄소 중립에 대해서
In Korea,
발표하고 탄소 중립에
we also announced a carbon neutrality goal to be achieved by 2050.
관련돼서
And
재생에너지
to this end,
전환이 일어나고
we are going through energy transition centered around renewable energy. As you know,
그리고 재생에너지
in order to achieve carbon neutrality and to increase the use of renewable energy, hydrogen plays a very important role.
한국에서 수소 수요가 약
We expect that the demand in Korea for hydrogen will
20만 톤 정도를
reach over 20 million tons by 2025, and we're going to import
하지 않기 때문에
a large proportion of the demand from overseas because we have limits in producing green hydrogen. So it is urgent for Korea to establish an ecosystem to import and utilize hydrogen.
에너지 저장 관점에서
From energy storage perspectives,
상당히 유리합니다.
Korea has strengths in terms of the battery, and
목표로 수소를
hydrogen is being selected as the material for long-term energy storage. And from hydrogen economy perspectives, hydrogen is very important. By 2050, the size of hydrogen market will reach about 2,700 trillion Korean won.
경제 성장 관점에서
So from economic growth perspective, hydrogen market will play a very important role.
한국에서는
In Korea,
수소 전략을 이렇게 나눴습니다.
this is our hydrogen strategy. First of all, there are technologies that should be urgently localized. Almost all the technologies related to production, storage, and usage should be domestically researched and produced.
수소 전략은
And Korea's hydrogen strategy is related to the hydrogen roadmap of the Korean government, the 2050 Carbon Neutral Declaration and Roadmap Plan, and 2030 NDC Upgrade Plan are all related to this hydrogen strategy. We have four categories. In terms of hydrogen production, we're focusing on green hydrogen, and we have two categories of hydrogen production technologies for the future. In terms of storage and transportation, hydrogen storage, delivery, and refueling technologies are under research and development. As for mobility, land mobility, marine mobility, and aviation mobility are included as the mobility-related hydrogen technologies. And fuel cell and combustion engines are also included as part of our hydrogen technology development plan. Our priority is to secure hydrogen supply technology, and through public-private cooperation, we'd like to create a market for hydrogen. In Korea, about 95% of the hydrogen is gray hydrogen. And in the case of Korea, our hydrogen industry is not fully developed, so we are lack of hydrogen infrastructure. In the area of fuel cell,
현대 넥소로 유명한 승용차
Nexo of Hyundai Motors
포커싱 돼 있고요.
represents
그리고
the passenger car using
다른
hydrogen.
차종들에서도
And
이제 그런 것들이
standards, laws and regulations, and certification standards for hydrogen are not fully developed in Korea. To solve these issues, first we have to localize the technologies to mass produce green hydrogen, and we have to create global hydrogen supply chain because we have to import a large amount of hydrogen from overseas. And we also need to develop hydrogen mobilities as well as standards and certifications.
원수도 전략의
In our hydrogen strategy, this is our vision.
마켓을
Our vision is to lead the 2050 global hydrogen market. In order to achieve the vision,
기술의 혁신이 필요합니다.
we need to innovate various hydrogen related technologies across the whole life cycle. We have three main strategies. First, we have to localize clean hydrogen production technologies. Secondly, we have to advance hydrogen storage and transport technologies. Thirdly, we have to advance the hydrogen usage technologies for mobility sector. Details will be explained in the other slides.
첫 번째로는
First, our first strategy,
환경수 생산 기술의 국산화가
localization of clean hydrogen production technologies.
수전에 그리고
It includes water electrolysis technology and next generation hydrogen production technology. First of all, we would like to localize the water electrolysis technology.
수도 공급, 수도 생산 가격의 인하가 가장
We have to lower the hydrogen production cost for this strategy. Korea's green hydrogen production technology has a gap with the level of advanced countries. We have two directions in this technology development. First of all, we have to develop core materials related to the system. In the case of the system, we will have to use the components and technologies adopted from foreign countries so that we could develop the relevant system. At the same time, we have to increase the efficiency of water electrolysis system. We have to improve the electrode, catalyst, and bipolar plate related technology improvement. And we are trying to increase the alkaline electrolyzer. And in the case of PEM electrolyzer, we are trying to reduce the cost. And regarding durability and performance of the system, and as for the stable operation of the system, we are making efforts, and we have also established the relevant plant. And we have lowered the hydrogen production cost. For example, we decrease the relevant cost and prices for producing hydrogen and cost for water electrolysis. SOEC and proton conducting ceramic electrolyzer are regarded as the next generation electrolyzers. In the case of AEM, anion exchange membrane is not yet developed. We need to develop a more highly durable anion exchange membrane. And along with this, MEA and relevant catalysts will be developed. In the case of SOEC, we have created 1 kilowatt level SOEC, and we're working on the stack up. The solid oxide electrolyzer technology is important because we need to create a product with high durability. We need to scale up the cell up to megawatt class level. For this, we are going to use modular stack design. And below 500 Celsius degree, we should produce hydrogen, and that will be enabled by proton conducting ceramic electrolyzer. For that, we are focusing on the development of the core materials. Besides these, except we have to work on the technologies except for electrolysis. For example, we have to use photoelectrolysis technology and the existing biomass or waste have also been used to produce hydrogen. From natural gas and biogas, we can produce hydrogen, and from waste, we can produce hydrogen. Relevant technologies are under development. Our second strategy, in order to import hydrogen to Korea, we have to work on the supply chain. This is related to the technologies of storing and transporting hydrogen. First of all, we have to develop technologies to store and transport hydrogen, which is imported from overseas. First, we can use ammonia, liquefied hydrogen, and LOHC. In Korea, as many of you may know, ammonia is quite much commercialized. We can immediately apply ammonia for hydrogen storage and transport. Ammonia synthesis is already a commercialized technology. We can decompose ammonia and produce hydrogen, and the relevant efforts are going on. In the case of liquefied hydrogen, we are lagging behind other advanced countries. But in order to import a large amount of hydrogen from overseas, hydrogen liquefaction is one of the priority technologies we have to secure. So we are currently trying to establish a hydrogen liquefaction process by 2030. And as for LOHC, in order to store and liberate hydrogen, we are developing the relevant materials for LOHC. In order to import hydrogen, we need to establish various hydrogen infrastructure, especially if we transport hydrogen on long distance, we need to establish a larger cargo system. We have to reduce the boil-off rate of the liquefied hydrogen. We are also trying to design the cargo system. And we need infrastructure for loading and unloading hydrogen. There is no such infrastructure in the world now, but we are going to develop such infrastructure. Regarding the domestic transportation of hydrogen, the road transportation, such as high-pressure trailer, is commercialized. It increases the pressure in the storage tank of hydrogen to increase the amount of hydrogen to be stored in the bank. And through cooperation with foreign countries, we have established a hydrogen liquefaction plant in Korea. And we are now developing a trailer to transport liquefied hydrogen. Once the development is completed, we will be able to transport them through pipeline. Currently, we are also working on developing pipeline. Now, city gas and hydrogen are mixed for transportation of hydrogen, especially as for safety, we are continuing R&D activities. And in the future, we are going to establish pipelines dedicated to hydrogen transport. Actually, our cost target is 400 million Korean won for 1 kilometer length pipeline. Currently, the price is about 1 billion Korean won. We are trying to lower the cost. And hydrogen refueling technology should be also localized. We are trying to make improvements so that we could enable high-speed refueling And we are also going to develop BOP for liquefied hydrogen station. And in the marine and aviation sector, we will develop technologies for hydrogen refueling. And in this effort, safety is very important. So, safety related international standards and the safety standards of hydrogen technologies will be further researched as well. And our last strategy related to the transportation and power generation based on hydrogen. In the case of electric vehicles, Hyundai's Nexo is leading the market. In order to advance this technology, we need to extend the driving range, and we have to increase the durability up to 300,000 kilometer. In the case of heavy-duty vehicle, the durability target is about 800,000 kilometer. In the case of HDV, Nexo is using 100 kilowatt stack up, and it is trying to create a 200 kilowatt unit system, which will then be applied to trucks in the future. In the case of next generation mobility technologies, for marine applications and for aviation applications like a drone, we will develop AEM. In the case of tram, we are focusing on enhancing the durability. In the case of the application for ships, there are coastal vessels and ocean-going vessels. So for coastal ship, we will apply 100 the kilowatt fuel cell system, and ammonia and liquefied hydrogen and various fuel-related technologies are currently being developed. And hydrogen power generation. So distributed energy supply system could be an example of this technology. Previously, we used the steam turbine-based power generation system, and modularization design could help it enhance the efficiency of the power generation system. We are trying to enhance the power generation efficiency by 60%, and the relevant efforts are going on, which will continue by 2030. In the case of gas turbine, we are developing hydrogen co-firing technology. We have to scale up this technology so that we could develop gas turbine dedicated to hydrogen by 2030. We have a lot of demand for thermal energy. Previously, we used fossil fuel to supply such energy, but we are trying to make more use of ammonia or other fuel. And this is our roadmap for each category among production, storage, transport, and usage. This is the summary. By 2030, we will develop electrolyzer and pyrolysis technologies and the relevant technologies for mobility as well. The Korean government is trying to allocate a large amount of budget for these activities. Thank you for your attention. Thank you, Mr. Yang, for your presentation. While listening to your presentation, we were able to understand the Korean government's plans and strategies for hydrogen technology R&D. For each strategy, he gave us detailed explanation. Thank you very much.
Now we will listen to the U.S. Hydrogen R&D policies and strategies. We will invite the principal analyst from Lux Research, Ronil Dahlia, to listen to the presentation on the U.S. hydrogen economy.
Hello, good morning, good evening, everyone. It's a pleasure of mine to be here to discuss the hydrogen economy in more details. A little bit about myself. My name is Ronel Dahlia. I am a principal analyst based at Lux Research. And for those of you who are not aware of Lux Research, we're an advisory firm where we help our clients, which are mostly oil and gas, chemical, and material companies, will help them navigate their innovation roadmap, their innovation decision, by providing information and advisory services in the areas of emerging technology. And at Lux Research, I am responsible for our coverage and advisory services in the area of the hydrogen economy. So first of all, I want to thank the organizers for inviting me to speak at this conference today. And today I wanted to spend some time, brief amount of time, to talk about the hydrogen economy with a focus on in the US. So looking at the hydrogen economy as a whole before I zoom in into the American landscape. So what is the hydrogen economy today, and what is the prospect of the hydrogen economy in the future? So what you see here is a very good projection of the hydrogen economy. Now, today we're at 100 billion tons of hydrogen produced every year. And all of that hydrogen is fossil in nature, and all of it is going either to the refining sector or to the fertilizer sector for the production of ammonia. But the question that we always get is, how big will the hydrogen economy be in the future? And it's very hard to answer this question because there are still a lot of uncertainties in this hydrogen economy. But the IEA, the International Energy Agency, last year did a projection of a net zero energy system. And in that projection, this is the amount of hydrogen that they expect will be needed by 2050. So today we're at 100 million tons. By 2050, we're looking at 500 million tons of hydrogen. So you're increasing your economy by a factor of 5. And what you can also see is that the hydrogen in 2050 will not be fossil in nature, at least a little bit will still be fossil, but most of it will be low carbon hydrogen, either blue hydrogen made from the consumption of natural gas with carbon capture, or green hydrogen made from renewable electricity through electrolysis technologies. So you can see here a projection of the hydrogen economy. Now, will we actually reach that 500 million tons per year capacity by 2050? If you're an optimist and you believe that we'll get to carbon neutrality by 2050, this is the amount of hydrogen we will need. But there are many scenarios where we also do not reach the net zero goal of 2050. So how do you interpret this figure? The way to look at it is to really look at the extremes. If there is no development in the hydrogen economy in the future, we will remain stuck at 100 million tons. If we reach our goal of net zero, we will be at 500 million tons. So these are the two extremes. The reality is that we will be somewhere in between 100 and 500 million tons of hydrogen per year by 2050. Now, what is the hydrogen economy? When people talk about hydrogen, about this economy, what are they talking about? Now, this schematic here really outlines the different stages of the value chain of hydrogen. So you begin with the production of hydrogen, and this is low carbon hydrogen, whether by natural gas with carbon sequestration or via renewable electricity. Now, once you produce that low carbon hydrogen, you have to store and transport it. Now, there are different ways of storing and transporting hydrogen. You can simply compress the hydrogen and feed that into a pipeline. Or if you're looking at international transport, you can also use options like ammonia, like liquefied hydrogen, or liquid organic hydrogen carriers. So there are various options for you to store and transport the hydrogen. Now, once you get the hydrogen to its destination, it's time to use the hydrogen. And here, there are different ways to use that hydrogen. You can simply burn it into a turbine for power production. You can feed it into a fuel cell for stationary electricity production, or in the mobility sector. You can use the hydrogen as a fuel in ships and maybe in the future in airplanes. And you can also use the hydrogen in the industrial sector. Today, it is being used in refining and ammonia, but the steel sector is also looking to be a major consumer of hydrogen in the future in their roadmap to decarbonization. Now, looking at this figure, you can see that there are many options for using hydrogen. So how do you distinguish between the two? And the way that we like to look at it here at Lux Research is to look at the value of hydrogen. Now, hydrogen has two values. It has the energy value and its chemical value. The energy value is where you're using hydrogen as a fuel. You're burning the hydrogen in order to extract energy in the form of electricity and heat. And in that area, hydrogen has a lot of competition. Hydrogen competes directly with wind and solar. It competes versus biomass, and it also competes versus other energy storage technologies like batteries. And in order for hydrogen to succeed, it really has to show that it is cost competitive with all of these different options, which is not easy. On the other hand, the chemical value of hydrogen, this is the most interesting one, because hydrogen has no competition when it comes to a chemical value. Now, the chemical value of hydrogen, how do you leverage that? It's about using hydrogen as a feedstock for the production of chemicals, but also, for example, as an oxidizing agent in the steel sector. Now, today you're making ammonia from hydrogen. If you take a molecule of ammonia and you remove the hydrogen, you replace it with something else, it is not ammonia anymore. So this is why the chemical value of hydrogen is so important, because in this area, hydrogen has no competition. So if you're looking at producing, let's say, 1 ton of hydrogen, and you wonder who do you want to sell this to, then in most cases, the chemical value of hydrogen, so applications where you can leverage that chemical value, will be the best market for you to go to. So this was a broad overview of the hydrogen economy, looking at the potential market for hydrogen by 2050, as well as an outline of the value chain of hydrogen. Now, focusing onto the US, what has been the latest activities, latest announcement that has really changed the landscape for hydrogen in the US? The first one, of course, was the infrastructure bill. Now, the infrastructure bill contained a provision where over $8 billion is looking to be funded into building the various hydrogen hubs across the US. Now, this is a very important development in the hydrogen economy, because if you ask anyone out there, how will the hydrogen economy develop? Not just in the US, but all across the world. A lot of times you will have people talking about hubs, hydrogen hubs. Now, if you look at Europe today, Europe is ahead of the US when it comes to the development of the hydrogen economy. The major projects being announced around Europe is really centered around this concept of a hub, where you start to produce a large amount of hydrogen and you target the existing applications of hydrogen, which is refining, chemical, as well as fertilizer. Now, once you build this hydrogen hub, where you can also develop mobility applications within the hub, this is where hydrogen can then filter out across the broader energy system. But you need to have a centralized location for the large-scale production of hydrogen in order to justify building small-scale applications around this hub. So this is why this investment, the potential investment into hydrogen hubs that has been offered by the infrastructure bill, has been really important to kickstart the hydrogen economy into the US. But the most important development is the one that happened this year, which is the passage of the Inflation Reduction Act. Now, it is a very large act, but part of the act was around providing incentives for the production of low carbon hydrogen. Now, this is really crucial because green hydrogen and blue hydrogen today are more expensive than gray hydrogen. And in order to justify a commercial investment in low carbon hydrogen in the US, you really need to have incentives. You really need to have these financial incentives, this tax credit, in order to offset that higher cost of green hydrogen, of low carbon hydrogen, that green premium really that you have from these projects. Now, what you can see here on this table is an overview of how much money really you will get. Now, the way that it works is that every hydrogen produced in the US, low carbon hydrogen, will be assessed by their carbon intensity. Now, if you have a carbon intensity, if your hydrogen has a carbon intensity between 2.5 to 4 kilograms of CO2 per kilogram of hydrogen, you'll receive 60 cents of credit, which you can take off of the production cost of your hydrogen. If you're lucky and you find yourself in that last category where you have almost 100% clean electricity or clean energy going into your process, you can get up to $3 per kilogram of hydrogen, which is extremely high, it's extremely significant in order for you to cut the cost of your hydrogen production. Now, how does that translate? $3 per kilogram of hydrogen is a lot of money, but is it enough to really promote the adoption of low carbon hydrogen in the US? So we did this analysis looking at the impact of the IRA on various production pathways for hydrogen, blue and green hydrogen. And for green hydrogen specifically, we looked at various sources of electricity going into the electrolyzers. Now, if you take a look at blue hydrogen, for example, you can see that the cost of blue hydrogen without any credit, just the cost of production for blue hydrogen, is at around $3 per kilogram of hydrogen. But if you include the IRA tax credits in there, assuming that you capture all of the CO2 or most of the CO2, then you're shaving off around 60 cents per kilogram of hydrogen. So then the total cost of your hydrogen is closer to $2 per kilogram of hydrogen. And for green hydrogen, you have various options for electricity. You can get hydrogen, you can get electricity directly from the grid, but unfortunately in the US today, most electricity is coming from natural gas or coal, which means that if you were to use grid electricity directly, you will not benefit from any tax credit because the carbon intensity of your hydrogen is more than 4. However, if you look at the other options for low carbon electricity, that's solar PV, that's onshore wind, geothermal, nuclear, and so on, you can see that based on the carbon intensity of these different electricity options, you can obtain tax credits. Now, if you're looking at solar PV and onshore wind, for example, you can see that the cost of production from these different options is higher than the others. Now, looking at solar PV in particular, why is the cost of solar PV so much higher than wind and geothermal? Now, even though the cost of solar electricity is quite cheap in the US today, the reality is that the capacity factor of solar is quite low. It's less than 30%, which means that the capital cost of your electrolyzer will be quite high. On the other hand, geothermal and nuclear, they have a more expensive source of electricity, but you're maximizing the use of electrolyzer, so the capex of your system is quite low. And if you're really lucky, if you manage to get zero emission electricity, where you can benefit from the full tax credit of $3 per kilogram, you can see that the tax credit itself offsets almost all of the costs of hydrogen production. So you can really see how significant the IRA tax credits are when it comes to green hydrogen. The tax credits shave off anywhere from 25% to almost 100% of the total cost of green hydrogen production in the US. And you're already starting to see the impact of the tax credit, the impact it is having. Last week, Air Products and AES Corporation announced that they will invest up to $4 billion in what will be the largest green hydrogen projects in the US. So that project, that facility, will be connected to 1.4 gigawatts of wind and solar capacity in order to produce more than 200 tons of green hydrogen per day. Now, this is still an announcement. The deployment date is all the way up to 2027. It will take time for both of these companies to secure the electrolyzer capacity and build that facility in the US. But what this really shows is that this project would not have gone forward unless there were tax incentives. Because the reality is that for this project to be successful, it cannot be competitive without this tax incentive. You really need to have these incentives. So this is the first major project that has been announced since the passage of the IRA. You can expect that many more similar projects will now be announced in the US. And looking at the current situation of the US compared versus the rest of the world, what you see here on this figure is an overview of the electrolyzer manufacturing capacity today and projected for the next 8 years, all the way up to 2030. Now, traditionally, the US has lagged behind Europe and Asian countries when it came to the hydrogen economy, which is why most electrolyzer companies today, even those based in the US, were looking at Europe and Asia in order to build their manufacturing facility for their electrolyzer cells. And you can see that until today, no one has really looked towards the Americas in order to build their electrolyzer facility. Now, this is data that has been announced, existing capacity and announced capacity before the IRA. Now, it is still unclear whether the IRA will definitely attract investment in projects deploying green hydrogen in the US. It's still unclear whether it will attract investment in manufacturing these electrolyzer cells itself in the country, but you can expect that this will happen. Because what the IRA has done, the IRA has made the US a much, much more attractive destination for any electrolyzer company out there compared to Europe and Asia. Europe and Asia, even though they have many countries in these regions have national hydrogen strategies, what they're lacking is really the incentives in order to attract these investments. So if Europe and Asia would like to compete with the US, would like to retain the dominance in this area, they really need to get started on announcing these incentives, on unveiling these incentives in order to keep the investments in their regions. Now, this was a very quick overview of the latest development in the hydrogen space in the US. If there's any questions, I'm happy to answer and elaborate on any of the points I made today. Thank you very much, and I look forward to hearing more from my fellow presenters. Thank you.
Thank you, Mr. Ranil Dalmia from Rox Research. We could understand what are the policies and strategies pursued by the US government to achieve the hydrogen economy. This brings us to the end of the first session on the hydrogen R&D activities of the two countries. Before we go into the second session, we will have 10 minutes of break. And at session 2, we will invite researchers from Korea and the US to listen to their recent hydrogen R&D activities. Please stay with us and let's meet in 10 minutes. So we will begin at 10 a.m. Korean time.
I'm glad to see you again. We're going to begin session 2. In the second session, we're going to listen to the R&D related presentations from researchers in different fields. In this session, we prepared 7 presentations. First of all, I would like to invite the researcher from Korea Institute of Science and Technology. Mr. Kim Jin-young will make presentation on materials interface engineering for membrane electrode assembly. Good morning, ladies and gentlemen. I am Kim Jin-young from KIST. First of all, thank you very much for giving me the opportunity to make presentation in this forum. I will begin my presentation. First of all, this slide shows the evolution of hydrogen fuel cell. Hydrogen fuel cell is being used as the engine for transportation means, especially when we use hydrogen fuel cell. It's different from the previous combustion engine. We can use hydrogen fuel cell as clean energy source for mobility, and many interest and R&D activities have been conducted in this area. Hydrogen electricity car is an example, and hydrogen bus, hydrogen taxi, and other mobility, including marine mobility and aviation mobility, are focusing on hydrogen as a clean source of energy, and R&D activities are being conducted actively. In the case of hydrogen fuel cell, it's not yet fully commercialized. In order to solve the issue, we need to develop the technology further. On the far right side of the slide, you see that the hydrogen cells are being actively used in transportation sector. If you go to the left side, you can see the steps for the stacks. In the case of the hydrogen fuel cell stack, depending on the output range, the area of cells or the number of layers could become different. In the hydrogen fuel cell, membrane electrode assembly is an important material. There is R&D going on for membrane electrode assemblies. Polymer electrode membrane is an important element here. If we secure the highly durable materials, we can use those materials to create membrane electrode assembly, which is the core element of fuel cell stack. As explained before, hydrogen fuel cells are being used as various sources of energy for mobility sector. The biggest research target is here. First of all, we need to achieve high performance, long lifetime in fuel cell. In theory, we can calculate the efficiency of fuel cell, but in order to realize the fuel cell efficiency, we have to optimize the resistance. So we have to decrease the gap between theory and reality in terms of the electrochemical resistance. Another important aspect of our R&D activities is related to the marine and aviation applications. Not only durability and lifetime, but also lightweight lightweight fuel cell is important. In order to achieve the relevant power output, we have to generate the relevant output, and at the same time, we have to make it lightweighted. We also have to reduce the cost. Actually, it's not just cost, but performance compared to cost. We have to lower the manufacturing cost. This performance will be a very important part in achieving hydrogen society. In order to achieve the cost performance, you can increase the power output or you can lower the cost for materials. There are two methods. Currently, we are trying to lower the price of the materials. So, through the use of hydrogen-powered fuel cell, I would like to introduce the applications in aviation sector. Recently, many interests have been paid to drone fuel cell. Fuel cell can be used as the engine for drone. Currently, drone has a large range of markets. There are both military use drones and civil use drones. And in the environment sector, many people are interested in using drone, and the drone market is rapidly growing. Annual growth of drone market is about 20%. And in the case of drone, combustion engine has been used as the main engine. From now on, clean engine should be used for drone. That's why we are focusing on hydrogen as the clean fuel source for drone, as the relevant information is stipulated in laws and regulations. Various research and development activities are going on for drone. We could use combustion engine, solar power panel, and lithium battery as well. For each technology, there are merits and demerits. In the case of gasoline engine, if we use gasoline engine for drone, it gives us high efficiency, but you should be worried about the carbon neutrality because gasoline engine emits pollutants, and it also creates serious vibration and noise. In the case of photovoltaics, it gives us lower efficiency, and if the weather is not fine, it will be difficult to use this, especially if you have to operate the drone at night. You will not be able to use sufficient amount of solar power. So solar power has limits in terms of the efficient operation of drone. Lithium battery is one of the most frequently used efficient energy source. But a lithium battery has low energy density. If you use lithium battery, it is difficult to make the flight time longer. Considering these issues, recently we have moved our focus on fuel cell as a possible source for drone. As mentioned before, in order to use clean energy as the source of the engine for drone, we are working on battery-related technologies. Battery has high efficiency, but it has limits in terms of the duration of the flight time. If you use battery, the maximum flight time of the drone is only 30 minutes. If you use hydrogen fuel cell, you can maximize the flight time of drone. Many people have high expectation for this, and across the globe, there are active R&D efforts for hydrogen fuel cell for drone. Many Korean companies have launched the hydrogen fuel cell for drone. In Korea, we have Doosan and Hyundai movies as well, which take great interest in hydrogen fuel cell for drone. They are trying to improve the performance and to maximize the flight duration of drone. So far, regarding hydrogen fuel cell, I talked about various research and development activities for land-based transportation. If you use this for aviation application, you can face potential issues. If you use this for aviation, you have to make the engine light. In order to use lightweight fuel cell stack, you have to use light materials and you have to optimize the BOP. If you use lightweight fuel cell stack, you can still face issues. For example, you will face severe dehydration phenomena, the drying phenomena, and it is difficult to manage water effectively if you use the hydrogen fuel cell for drone. So you will see some loss of energy. In conclusion, in order to achieve lightweight fuel cell for drone, you have to simplify the system, and in order to ensure good performance of the fuel cell, you need to maintain a proper level of water inside it. And if you make it lightweight, then you will face limits in effectively managing water. So, we have conducted research activities to understand the dynamics of water and improve materials for this system so that we can operate drone even under non-humidified environments. In order to maximize the performance of hydrogen fuel cell, we have various strategies. First of all, based on theory, we are trying to develop and design materials that will make the up drone fly effectively. So we are conducting R&D on electrolytes and electrolyte membrane as well. And we are trying to manufacture the fuel cell stack based on the proper membrane materials. Besides them, we have plans to enhance cost of the materials, not only the performance improvement. For example, we have to lower the price of catalyzers and the membrane, and we will have to conduct R&D on maximizing performance and in order to optimize the flight time of drone, we are researching various types of materials, and we mounted the materials we developed on the drone and tested it. These are the images of what I have just explained, and if you compare our fuel cell stack with the commercial fuel stack in the market, our fuel stack shows much higher performance. And we mounted the fuel cell stack we developed on the drone, and we had two payloads and operated the drone and tested the flight time, flight duration of the drone. And we are continuously conducting R&D activities to optimize this fuel cell materials. Thank you very much for your attention. Mr. Kim Jin-young, thank you very much for your presentation. Thank you for explaining about what kind of R&D activities you are conducting, and thank you for explaining about the applications of hydrogen fuel cells, especially in the aviation sector. YouTube audience, if you have any question, please leave your question in the chat box. We can answer those questions during panel discussion session.
Now we will invite Professor Jang Seung-soon from Georgia University, and he will be presenting on the multi-scale modeling and simulation approach towards new material development from polymer electrolyte fuel cell. An apology. Well, it seems like the professor has not signed on to the Zoom yet, so please bear with us. Can you hear me? Yes. Yes, you're connected. So, Professor, please continue. Thank you very much for giving me this chance to present on my research topic at this very important forum. Can you see my screen? Yes, I believe you can see it well, so I will continue. My presentation today is actually what was briefly mentioned by other presenters, including the previous presenter, researcher Young Kim. So, for what are the materials that we can develop for the fuel cell development? In order to have the fuel cell developed, the hydrogen economy is very important. Of course, I think that everybody understands that, but from which source we create hydrogen will determine whether we can create blue hydrogen or green hydrogen or turquoise hydrogen. And we have to also transport and distribute the produced hydrogen to desired locations. And in the end, we should be using the hydrogen to create electricity to put it into the fuel cell. So that is the end use technology that we need to develop. So today my presentation is about this end use application, the fuel cell, and what are the materials that we can use to create fuel cell, how we can design that to achieve the desired performance. These days, the fuel cell technology is somehow competing with the battery system. However, the battery technology is focused on how to store energy, but fuel cell is how we create energy from source. It's like energy conversion technology. So whether fuel cell is better or battery is better, it depends on what we use as the material to create the desired equipment. So the argument can depend on the specific situation. For now, we have the automobile market where the battery is more advanced than fuel cell. However, the fuel cell is also developing its own materials and technologies. So I think that in any time, in any industries, including the automobile, a fuel cell could take the lead ahead of battery. So during my presentation, at my lab, we study fuel cell, battery, and also photovoltaic energy technology as well. But for my presentation today, I will be focusing on fuel cell. So fuel cell is not a whole new technology, but as you can see here, in 1615, it has developed from very long time ago for the spacecraft in 1965. But today it is gaining attention in the engineering sector so that we can commercialize in the automobile sector. So in the past, we were operating cars with the IC engine, but if we advance fuel cell, then it would have potential in the automobile segment as well. And in that regard, I want to talk about what we can do to improve the fuel cell technology to use the materials that we want and to enhance its performance. I will not be going into too technical elements, but give you just a broad overview. So you can see this energy flow. If we put hydrogen as the energy, then at the catalyst, you can see the letter H plus, it is converted into proton. So proton goes through this blue part, the membrane, to go to the other side of the catalyst. It's called cathode. It goes to cathode, and it meets with oxygen that we get from air and meets the water to complete the electrolysis. And that is how we keep on with the energy supply, and electricity is generated through that process. So if I zoom in to the slide, this blue part is the proton exchange membrane. There could be other exchange membranes like alkaline membrane, and there are researches being carried up about those different kinds of membranes. So if you look at the right bottom side of the slide, you can see that the water has polymer in it, and the blue thing in the cube is water, and through the channel, that water channel, H plus the proton is transported. So that is the role of the polymer electrolyte, and this is what I'm going to focus on today. And of course, I will be touching on a catalyst and other elements where we are also developing new materials, but I think that I will not have enough time to talk about that, so I will be focusing mostly on membrane. So in order to create a good membrane to achieve that target, how should we carry out the research and achieve that target? Well, first, from scientific point of view, this 100 nanometer, well, nanometer is such a small scale that is even smaller than the meter. That's like a unit that we use to measure those small units. And if you measure this membrane with the nanometer unit, you can see this water channel in the small membrane. And here you can see the flow of water and proton. And if you zoom in once again, then you can see that polymer electrolyte and water creates phase. And through the interaction, their borders are like the water and oil. They have total segregation of the phase. So whether they create this kind of clear border of segregation or whether it is somehow mixed can affect the performance. So how we can control that segregation is another task. And you can zoom in, you can see the zoomed in photo in the center. And to control all those factors, we have the chemical composition or configuration that can allow us to make very refined adjustment. So we zoom in more and more to look into smaller element and structure to fine-tune the control. So in 100 nanometer, from 100 nanometer to 1 nanometer in various units, we are trying to have diverse controls. And during the process, there are various methodologies that we can employ. So at the molecular level of 100 nanometer, we can utilize the quantum mechanics, QM, to achieve the performance enhancement and characteristics enhancement. And based on that, we can have like the number of nanometers or dozens of nanometers level of fine-tuning that is done through the statistical mechanics SM. And I mentioned about the water channel that is distributed together with the polymer electrolyte. And at 100 nanometer for that level, we can also look into their structure. So based on which structure or which unit we look into, we can have various methodologies to be employed for our research. So this is another zoomed in photo of the water channel distribution at the bottom. So in this area, the champion material that we are very accustomed to or has the best performance are indicated here in the chemical formula. So that is naphthalene. And naphthalene has its own benefits, but of course its drawbacks. So to overcome those drawbacks, we are doing our research. Through computation, we are doing the research, and during the process, we can utilize the quantum mechanics and statistical mechanics and various other methodologies as well. So for here you can see naphthalene 117, that is the polymer. What are its drawbacks? First, it is too expensive. So if you compare with gold, it is actually as expensive as gold. So if we employ naphthalene in fuel cell, the fuel cell price will go up. And naphthalene has strength in proton transport, so we have to find a cheaper material with the same proton transport performance. And for the water channel, when the temperature goes up or down, or if the water boils or freezes, it can impact the performance in the fuel cell. So for how we can control that is another requirement. So of course there are great materials that are already identified, but still we need to discover more new materials to achieve the best performance. You can see SPK at the bottom. So we can compare SPEK with naphthalene. For naphthalene, the water channel is in between the green polymer. It's specified as SPK. You can see that the water channel is broader than SPK. So it means that through that wider water channel, it delivers better performance. Proton goes through the water channel, and I will explain that briefly through this photo. On the right side, you can see the big blue ball, and that is hydronium proton, one kind of proton, and there is this hopping phenomenon where hydrogen goes to one of the water molecule next to it, and then goes to the does the hopping again to go through the membrane this way. But how we can facilitate this well is our purpose. So this is called hopping. And this is the animated video that we have prepared to explain this hooping process better. You can see that this small molecule is hoping to get transported through the membrane, and how we do this better is one of our objectives. So you can see that if this is done nicely, then as you can see at the bottom, it will be like very smooth traffic in the highway where we can have very nice transport. But if that is not done nicely, we will have very narrow alley where a lot of cars are trying to move. So this was just an example that I have prepared to illustrate the purpose of this water channel and the movement of proton to achieve higher performance. Here, I'm going to go back to naphthalene. On the left side, you can see the photo, and on the right side, that is also naphthalene structure, but there was a little bit of structural modification made to the naphthalene. On the left side, you can see that the proton transportation is better on the left side compared to the right side. So even if it's the same material, based on the adjustment or engineering that we do, it can show different performance. So that was validated through our research, and we are applying this to the material design and application. So at the top, you can see how to improve the proton transport. That is one of the objectives. And to do that, how to improve the water management, how to reduce the production cost. And if there is like even if there is a great material, if it doesn't have great ecological footprint, then we will not be using that material of course. So those diverse objectives should be achieved in developing the new material. So we have been focusing on those elements and we will continue to do so. So at our lab, we have developed these materials that I have explained. And as the previous speaker has mentioned, not just proton exchange membrane, but also other kinds of exchange membranes are being developed and studied. So I believe that better performing membranes will be discovered and employed. Of course, there are diverse materials, and fuel cell can be developed by using that. And to have great desired performance, we have to have research on catalyst to find out whether additional fine-tuning can be done for catalyst. So you can see here, this is one part of the catalyst. We have zoomed into one small part of the catalyst. You can see that there is platinum, that is the main catalyst being used. But of course, I believe that there are studies being carried out to identify better performing catalysts. And here you can see how polymer is binding with the catalyst to achieve higher performance. And through the process, if when hydrogen is achieved or proton is achieved, how they should be transported to generate more power are being studied as well. So there are various interactions being made to create great combination between materials that we are using. So this is one of the fundamental studies that we do. And you can see on the left side the animation based on the actual temperature, the actual operating condition. You can see how those elements are being transported. So this is one of the predictions that we can do before carrying out the actual experiment. So this is the end of my presentation. So I have said that we are using multi-scale modeling for the fuel cell system so that we can have higher performance and also be more eco-friendly and have cheaper production cost. So that is the summary of my presentation. Thank you for listening. Thank you, Professor Chang, for your presentation. Through your presentation, I could understand the multi-scale modeling approach to have very accurate interpretation and prediction of the fuel cell systems.
Next presentation will be made by Mr. Kim Sang-kyung from Korea Institute of Energy Research. R&D activities in PAM and AEM electrolyzer at Korea Institute of Energy Research is the title of the presentation. Mr. Kim Sang-kyung is not yet ready to make presentation. Please wait for a moment. Please share your screen. Are you connected to Zoom? I can hear you. Please share your screen. May I begin my presentation? Yes. Please go ahead. Today I am going to explain about PAM and AEM electrolyzer R&D activities. First of all, I will briefly explain about our institute and further details about what we do here. We are located in Daejeon. In Buan, Gwangju, and Ulsan, we have research centers. We have about 1,100 employees and our budget is about 210 billion Korean won. We are researching renewable energy, hydrogen energy. Today, I am going to talk about the fuel cell and hydrogen-related energy R&D activities. I'll briefly explain about our R&D on PEM. One of the biggest issues is the iridium catalyst. The amount of iridium is very critical in the research and development activities because depending on the amount of iridium, it could cause resistance and poisoning as well. So we are trying to use iridium that could minimize the acidification and that could minimize resistance. Also, we are focusing on electrical conductivity and strong corrosion resistibility and high electrochemical stability. If you conduct synthesis, we need to optimize the synthesis like this. So you can see the different sizes of particles. If you look at the graph here, it shows oxygen evolution reaction activity. Regarding the charge, and in terms of durability, so please refer to the chart and table for our research and testing on durability of the materials. So I have to move to the next slide. Actually, the slide is not working, so I think I just have to move on with my presentation. And we try to find the reason from SDX. And I think I talked about temperature. So we conducted the synthesis like this. 60% and 40% is the figure we got here. This is called anodic charge. So please refer to the chart for our performance in the test. And we conducted the XPS analysis of the iridium. We used 0.5 milligram iridium, and we used different amount of iridium to see the result. And we saw that the anode, we also measured the anode catalyst loading and saw how the current density increased. And we also tested how the cell voltage changes as time passes. Sorry that in my computer the slide is not working. Secondly, I would like to talk about the loading of iridium. So we wanted to see the normal performance of the catalyst by adjusting the amount of iridium. We sputtered the platinum on the anode catalyst layer. And we sputtered 80 nanometer and 40 nanometer platinum on the anode catalyst layer, and we sputtered up to 80 nanometer platinum on the membrane as well, and saw what happened. In the first case, it shows a certain level of performance which goes down as time passes. In the case of 80 nanometer and 40 nanometer, you can see that even if we use a small amount of iridium, the performance was not bad. This is when we use the large amount of iridium. This is when we use the small amount of iridium. When we use the small amount of iridium, you can see a different performance. So we were able to see what kind of role the platinum plays on this layer. Next, we applied this to the wind power. This is the power data from the wind power plant. And we run the wind power and got the data for 30 days. And we emulated the current density for 1 day and applied this to our cell. Sorry that my slide often stops. We compared 3 things: custom current, and we compared the fluctuating currents, and we compare different cases with different level of frequency and a different level of intensity. In terms of theory, this is the current fluctuation. I'm sorry, I cannot move to the next slide. So we compared custom current and wind power. And the main reason that we saw the result, as you see on the graph, was the ohmic resistance. And you can see how this is related to the frequency level. And main reason for this result was ohmic resistance. The other slides show the results of our testing. Here we faced another issue related to the membrane thinning. In the wind power, we were able to see the membrane was getting thinner and radical was formed. Now I'm going to talk about AEM water electrolyzer technology. In terms of the AEM electrolyte membrane, we wanted to achieve chemical stability as well as thermal stability. In the case of the polymer, it's difficult to use the membrane. And in this case, we use the ion conductivity to increase the durability. So this is the way we designed this membrane. I'll show you the result later on. Next one is non-precious catalyst for AEM electrolyzer. And we were able to see the performance was getting better. And perovskite oxides were also combined for the catalyzer. In the case of the AEM electrolyzer, in the first case, it was cis type. So we tested this. In the case of the membrane that we developed, it showed similar performance with platinum, and I think it requires further research and development. This is CCM type electrolyzer. We compared this with the electrolyzer we developed, and it shows similar performance. At higher temperature, you can see a little difference between the two. And if you compare the two graphs, you can see there was a little difference in the terms of the performance between the one we developed and the electrolyzer you can get in the market. With this, I would like to conclude my presentation. Thank you.
Thank you for your presentation. I could understand what are the PEM AEL electrolyzer release studies carried out at KIER. And I'm very sorry that we had technical glitch during the presentation. Once again, I want to make the announcement. If you are joining us on YouTube, if you have any questions, please write in the chatting so that we can ask those questions during the panel discussion. We will go to the next presenter. We have Mr. Capuano from Nel Hydrogen. he will be presenting on the title of taking electrolysis to large scale. The next presenter, Director Kapu Ano, is joining us from the US. So we would need to give him some time.
I think I'm okay.
So are you
I think I'm
ready?
to go. Yep.
Yes.
Yes.
Yes, please go on.
Hi. So, Christopher Capuano from Nel Hydrogen in the U.S. The talk I'm going to give today is really what we're doing as a company to try to reduce the cost of hydrogen to make it more accessible for these emerging energy markets. So most of this is focused on some of our manufacturing scale-up activities, with a little bit of some background on the R&D topics that we're covering as a company. So Nel Hydrogen is a global company, the largest pure electrolyzer company in the world right now, where we have 3 different locations, one in Norway that's doing alkaline electrolysis, where I work in the United States that's doing entirely PEM electrolysis, and then a facility in Denmark that builds fueling stations, complete infrastructures all the way from compression and storage to dispensers. So the areas that we try to feed into historically have been industrial applications as we've waited for the hydrogen economy to really start to take shape. So we've been able to work on really the high durability of our products to serve into those industrial markets while we waited for the hydrogen economy to start to take shape. And all of the markets that we've discussed today, all of the applications that we've discussed today are the same areas that we're working to try to get better penetration into with our products, and that is hydrogen fueling stations. We're going to continue to work as an industrial gas supplier for any application that might need a reducing environment. Transportation into both light and heavy duty vehicle applications, and then power to energy applications. So as I mentioned, we have 3 different locations throughout the world. Where I work in the United States is in Connecticut. We are about 150 people currently, and in our current capacity, we can build about 50 megawatts of PEM electrolyzer capacity currently. But we're in the process of scaling up the existing facility to be able to do 150 megawatts annually. Our facility in Norway that does liquid alkaline research just commissioned earlier this year a facility capable of doing 2 gigawatts of liquid alkaline capacity. Currently, it's only sized at 1 gigawatt, and we will add those additional lines to increase the capacity in the next year or 2. And in Denmark, our fueling station facility can do 300 full fueling stations a year with the current configuration. So as I mentioned, the plant that in Norway that does pure liquid alkaline electrolysis is a completely automated facility. It allows us to handle much larger format components while also increasing the throughput of the systems. And so this is going to serve as the model for all of our future installations. I think I mentioned this in one of the slides coming up, but in the United States, we are currently looking for a site to begin the manufacture of a 2 gigawatt PEM facility, and it's going to use the Norway facility as the model for that. You can see some of the images that we have in the top right is the building in Norway. The bottom left image is the inside of the facility and one of our coating lines in this continuous automated process that's been implemented. And then just from a historical perspective, and alkaline is probably still one of the preferred technologies to be able to generate green hydrogen because it's been around for a very long time.
Mr. Capuano,
Yes.
could you check your mic, please? Because it was hard to hear your presentation. So could you check your mic, please?
Yeah.
Yeah.
Maybe if I get closer, this will be a little better.
Yeah.
Sorry about that. So So as I mentioned, Nel Hydrogen has the broadest electrolyzer portfolio to bring to the market. We have electrolyzers for all the way from 3 kilowatt systems up to 100 megawatt and larger. We recently installed a 20 megawatt PEM facility that's making green hydrogen into an ammonia synthesis plant in Spain. And we also have an order for a 200 megawatt system in the United States for a liquid alkaline system feeding into an industrial process. Our fueling system, our fueling technology, as mentioned, takes everything from the beginning of the compressor phase all the way through supply, fueling, and storage to our dispensing module, where we have the configuration to be able to fill up to 10,000 psi, 70 megapascals of direct dispensing to both light duty and heavy duty vehicle applications. The systems as they're designed, we would prefer to have an electrolyzer in front making the hydrogen for the system, but the way it's configured, we're able to accept any form of hydrogen as shown in the slide here. Reformed gas, liquefied hydrogen, and gaseous hydrogen can all be used in place of an electrolyzer system. So the PEM installation that we're currently configuring for the United States is going to be phased in similar to what we did in Norway, where we're going to begin with a 500 megawatt line in a 2 gigawatt scale facility. And as the market increases and as demand increases, we will add additional capacity within the existing plant all the way up to a 2 gigawatt design. We should have that location identified by the end of this year. So a lot of the work that we've been doing as an engineering group, in addition to pure fundamental research, we also have to do research on taking those technologies from small scale and be able to translate that performance that we experience in a really small form factor into very large scale and thousands of cells over and over again, and maintain that pure quality and maintain that performance so that these energy storage markets that are very, very sensitive to efficiency and lifetime in order to be able to recover the cost of their investment, we really spend a tremendous amount of time designing and developing these systems for scale up and implementation into a fully automated manufacturing process. So when the company was first started back in 1996, and I've been there since 1998, we were sold this vision over 20 years ago that the hydrogen economy was just around the corner. And a lot of us waited and waited and waited. And while we waited for the opportunity that we have in front of us today, we were able to really focus on improving the durability and the design of our systems over that period of time. So when the markets became available, we would be ready to take advantage of that. How we did that was pursuing relationships with our Department of Energy, our advanced research federal agencies, to help us with the incremental research and development activities required in order to make the products cheaper and more efficient. As a small startup company, that was very, very difficult. We didn't have a lot of money to support some of that early term development. And so we looked for our federal agencies to provide us research grants to be able to accelerate some of that development. And the slide that I have here now is a snapshot of some of the different projects that we've used over the past 10 or 15 years to be able to use the output from some of our fundamental research grants and apply those to our commercial devices. And so there's been many different federal grants that we've received where we've been able to use those to do the research that we needed to perform as a company and take the output from that and apply it directly into our electrolyzer devices. And they're very they're the type of research projects that you would expect. Looking at cheaper membrane, thinner membrane to reduce the ohmic resistance to improve the efficiency. How do we reduce the amount of precious metal content within our systems, but still be able to maintain the same efficiency and durability and performance in order to reduce cost? And I would say that we've been very, very successful in turning these opportunities into products for the company. And it's really been what's able to allow us to maintain ourselves as a company until we've been able to get to where we are today. So we're not going to be able to reduce the cost of our systems entirely by just automation. So there are several different steps along the way that we are going to implement in order to drive down the cost. And the first one is on the technology side, and this does include scale up and automation, but it really looks at our cell stack. And this is an effort that we're going through now. And instead of just designing a cell stack, we're designing a cell stack that really has automation in mind. So all of the components that go into it, all of the separator plates, the gas diffusion layers, the membrane electrode assemblies, we will design those from the ground up with the understanding that what we have at the end needs to be easily brought into an automated manufacturing process. Most of the cell stacks that we have today are handmade. The parts that we use reflect that. They're very, very easy for a technician or an operator to handle those and place those into a cell design over and over again. The next cell stack will not look like that. It's going to be designed where an operator will not have to handle the parts themselves. Everything will be through robotic automation or a continuous assembly line for processing of the components. On the engineering side, we are looking at scale. So we're taking some of our existing platforms and trying to determine how we can package those differently in order to use a base module and configure those so you can add them together in order to get to the end user's final requirements. And then procurement, one of the areas that we've really started to work on is through our supply chain. And as we become a larger company, it's become much easier for us to engage suppliers in order to get cost reductions through volume purchases or work with them on long-term strategic plans in order to try to help us reduce the cost just through supply chain management. With those activities combined over the next couple of years, we expect that we're going to be able to reduce the total cost of the electrolyzer and balance of plant by about 40% from where we are today. And we would expect this to happen probably by 2025. So on the more fundamental side of things on the cell stack, I have an example here of where we have looked at targeted cost reduction from a capital expenditure point. And so as I mentioned, we don't just do manufacturing and scale up and automation. We do a lot of fundamental research at our facility. And what we've been able to take advantage of are the national labs in the area, some of the universities that we've partnered with, and we've looked at components within the cell stack all the way back to component modeling, where we do fatigue analysis. We do computer-aided modeling to try to understand how we can optimize the designs for these. We look at flow fields for water distribution, heat management, and we've had universities help us with the thermal modeling of some of these components so we can understand the configuration that we need to have for flow fields for adequate heat removal while still maintain the adequate flow to the cell and the reaction while trying to remove the oxygen that's generated away from the electrode interface as well, so you can continue to provide reactant to the interface. Materials of construction is a large area that we're looking at right now. We are constrained by a very small list of materials that can go into our cell stack due to the high potentials in an oxygen-rich environment. Most of those are titanium. Titanium is still sensitive to hydrogen embrittlement, so we also look at coatings of those pieces of material in order to extend the overall life of the system. And since we've been building cell stacks for over 25 years, we have a fantastic mechanical engineering group that's really been with us for quite a long time and has a rich history in stack design. And so what we've been able to do as a company as we've scaled up our designs from, say, 100 square centimeter active area to what we have today, which is almost 1,600 square centimeter active area. All of our cell stacks have a very, very similar architecture on their repeat and cell assembly. So what that's allowed us to do is a significant amount of our testing at the very, very small subscale feasibility range using a platform that has an equivalent cell configuration as to the large form factor. So we can keep the cost fairly low by doing most of our testing on the 100 square centimeter size. But because the other cell platforms that we have share an identical architecture, the translation at small scale is much, much quicker to go to those large form factors without having to incur the high expense of building a 100 megawatt cell stack test article. And so as a company, we obviously always question as to whether or not we can truly get to the targets that we need to as a world organization here in terms of dollars per kilogram. And so the plot that I have here says that we can get there. But we really need inexpensive renewables to enable that. And so the purple line that I have on the graph here really shows the cost reductions that we expect to realize purely through technology advancements and purely through cheaper designs for our cell stack. And you can see that even with all of those cost reductions, we never quite get to $4 a kilogram or so, where the red line is. It will asymptote and flatten out across the top of it. So we need the traditional grid-powered electricity cost to come down, and we believe that'll happen through the widespread adoption of renewables. So immediately, if we, you can see the red line, which is what the Department of Energy has us use as a standard pricing for grid-based electricity, which is 5 cents a kilowatt. It gets us to about $4 a kilogram. As soon as you start to deploy renewables and can get to something closer to 2 cents per kilowatt hour, you can see what that does to the total cost. There's a significant improvement on the operating expense realized by that reduction in cost of electricity, where now we're looking at about a dollar per kilogram at the cell stack. So it doesn't include the balance of plant. We believe we can get to $1 a kilogram with just cell stack cost. This is just another way of really looking at what I just went over. So you can see through the plot in the top right, as we scale our systems and we go from 5 kilograms a day all the way to 500 tons a day, we start to get very close to 50 cents a kilogram for the balance of plant for the system. And so we believe that with scale alone, we can get very close to 50 cents a kilogram on the balance of plant on the system. And then if we get the electricity cost down to 2 cents per kilowatt, we can get the operating expense down to $1. And that gets us down to our $1.50 per kilogram target that we've set as a company to meet by 2025. I just have another slide or two here, and I'm just about done. But I just figured I'd touch very, very lightly on some of the R&D areas that we're working on as well. And a lot of this has to do with porous transport layer development and electrode development. So as a company, as we move towards automation, really what we're looking for is to take advantage of some of the manufacturing techniques that have been developed by the fuel cell industry. And this is roll-to-roll manufacturing of electrodes onto membrane. There's a lot of development because no one's really looked at, there's not a lot of research that's been done on coatings with oxide-based electrode inks. The platinum side is fairly straightforward because there's a lot of literature out there on how to do this from the fuel cell community. So where we've spent a lot of our time is on the oxygen evolution catalyst and trying to create a suspension using iridium oxide catalyst, and then implement that within a continuous manufacturing process. You can see the image that we have in the top middle. Shows a very, very, very nice uniform thin layer of catalyst that we're able to deposit with this with this roll-to-roll manufacturing technique. And what that allows once we move to an automation process for our MEA manufacturer is it takes our baseline cost down significantly. And that's done through the reduction or the lowering of catalyst loadings, because now that you have a piece of automated equipment and have taken the manual process out of it, you can more accurately control the deposition that you're putting down, so you can create a nice thin, lowly loaded layer. What it also allows you to do is look at using thinner membranes. Thin membranes right now are very difficult for an operator to hold. Once we put that into a roll-to-roll automated process and it's not being handled by a person anymore, you can start to put thinner membranes in there because they're not, the handling time is significantly reduced. The other side that we're looking at is to improve the interface on the oxygen evolution catalyst. Typically, what we've used is a porous transport media. It's a sintered titanium plate, very highly porous because it needs to be able to get water through to the electrode, but it also needs to provide a mechanical support in a hydrogen pressurized cell. The problem with that is the surface of the porous transport layers is very open. It's about 50% porous, which means that you have a lot of open space in that porous transport layer that's not making direct contact with your electrode. And that means that you have catalyst in the electrode that's not active and it's not being used and it's being wasted. So what we're looking to develop, and we're in the middle of halfway through a project funded by our Department of Energy, is put in a microporous layer on the surface of that porous transport layer. A metal, a titanium microporous layer to be able that represents essentially a denser structure at that interface that provides a nice continuous layer to engage your catalyst layer, but will still work to be able to move water to the interface and remove oxygen from the surface. And so if we have that nice dense structure at the interface, we can continue to reduce our load-ins and go thinner with the electrode because now we have a much higher percentage of catalyst in contact with your porous transport layer using all the materials that you have put down. So this is my last slide. I appreciate everybody's time tonight. So as I mentioned, we have a very long history at Nel. It's 26, 27, 28 years old, and I've been there for 25 of them. We have really, really great reliability in our products, and it's showing because we really have received quite a few very, very large scale orders lately based on our past experience with our industrial gas partners and recommendations from them. We have clear roadmaps in order to get us to the price targets that we need as a company and what the community needs for this technology to be able to be implemented. And we have a lot of really inspired and driven people at the company that are working to make sure that happens. So with that, I think that was my last slide. And I can stop sharing.
Thank you for your presentation, Director Capuano. We could understand all the PEM-related researches being carried out at Nel Hydrogen. And once again, apologies for the sound problem we had during the presentation.
Next presentation will be made by Mr. Park Byung-ha from Korea Atomic Energy Research Institute. The presentation title is Coupling of a High-Temperature Gas-Cooled Reactor to a Hydrogen Production System. Good morning, ladies and gentlemen. My name is Park Byung-ha. I am working in the Nuclear Hydrogen Research Team at Korea Atomic Energy Research Institute. Thank you for inviting me to this forum. And I am going to talk about how hydrogen can be produced through gas-cooled reactor. I'm pleased to have this opportunity. High-temperature gas-cooled reactor is being developed by my team. And today, my topic is related to our R&D activities. And I'll talk about nuclear hydrogen production. Especially, I want to focus on 30 kilowatt SOC test bed. First, let me explain about Korea Atomic Energy Research Institute. Our institute is the government-funded institute researching nuclear technologies. In the past, we focused on localizing nuclear technologies to develop TPWR, steam supply systems, and reactor localization technologies. And these days, we are trying to develop advanced reactor technologies. Especially among advanced reactors, a very high temperature gas-cooled reactor is an important one. at a very high temperature, we can produce heat to produce hydrogen. First of all, let me share with you the current status of nuclear power in Korea. We have 24 nuclear power plants in Korea. As you know, nuclear power generation is important to reduce greenhouse gas emissions in the energy sector. Low carbon energy like solar power and wind power have been developed so far for the past 10 years. But in the heavy industry sector, in order to get heat and electricity, many of them depend on fossil fuel based energy. For example, over 40% of the industries in Korea, for example, POSCO and steel-making companies are generating about 40% of the carbon emissions in Korea. In order to solve this problem, steel-making companies are trying to produce steel by using hydrogen. And the relevant technologies are being developed. For example, fuel cell, SOC, solid oxide hydrogen-based production technologies. Not only steel-making companies but also petrochemical companies in Korea are under pressure to reduce carbon emissions they make, and petrochemical companies have been using fossil fuels and now they have to reduce the use of fossil fuels. So as a new source of energy, they have clear demand for hydrogen. So nuclear power serves as the source of power for electricity, but also as a source to produce heat and electricity, especially high temperature gas can be used to produce heat and electricity. So the energy produced through nuclear power plants can be applied to petrochemical industry. This is the overview. Among high temperature gas cooled reactors, we are developing very high temperature gas cooled reactor. The VHTR, the very high temperature gas cooled reactor, is optimized to nuclear hydrogen production. This is different from the reactor that produces electricity. It uses helium gas as a cooling gas to eliminate heat, and it provides heat to the hydrogen related power systems. And VHDR is used for producing hydrogen. The heat delivered from helium is over 900 Celsius degree. Such heat can be used in steel-making companies. The 900 Celsius degree is a very attractive temperature to the perspectives of, for example, steel-making companies. So in order to develop the VHDR, we started R&D activities since 2014. The very high temperature equipment are used under very special and unique environment. So we have the experimental loop dedicated to this, and the hydrogen production technology has also been under the R&D activities at our institute. These are our latest projects. Nuclear power and hydrogen coupling technologies, including designing technologies and materials development technologies, are under R&D. And high temperature water electrolysis and high temperature gas-cooled reactor coupling technologies are under R&D activities. This facility is our comprehensive test facility for HTSE. The photo here shows our high temperature test loop that emulates high temperature gas cooled reactor. By using this test facility, we simulate the operation of very high temperature gas cooled reactor. Through water electrolysis, we produce hydrogen. We have just finished constructing this test facility. This facility can supply up to 850 Celsius degree steam from helium gas. We can also use waste heat. If you compare the level of heat this facility provides with the level of heat from waste heat, our facility provides high temperature heat with low current density. So we expect that our facility could improve the lifetime and efficiency. And our test facility has operational capability of 30 kilowatt electricity output, and we are trying to conduct integral tests using 6 kilowatt modules. And if we can get a partner for this, we can increase the operational capability. But this test facility itself can test up to 2 mega SOC stack. So our test facility provides state-of-the-art test bed. It could be a good opportunity for various SOC partners. For SOC integration, this facility can be used as an excellent test bed. And while developing nuclear technologies, we have acquired various relevant technologies. The example is on the right side. On the picture, you see multi-stream printed circuit heat exchanger. This is small, but under a high pressure environment, it can exchange heat. So helium, steam, and air should be exchanged with each other through this exchanger, and it can increase the temperature of the steam up to 850 Celsius degree. And meanwhile, this is the process related to nuclear power, and safety is the most important priority. We are trying to check safety in the coupling and collocation of HTGR and HTSE. So we are working on the design of this coupled system, and we're trying to see how this coupled system works and how this could work at commercial level. We are analyzing this aspect. And reactor creates the source of heat. So we can apply this technology to other industry applications such as steam methane reforming and naphtha cracking. So we are expanding the scope of our R&D activities. Currently, we are partnering with Pohang Institute of Industry Research, which is called LIST. We're cooperating with LIST for SOC stack. LIST is in charge of producing SOC cell. It is also conducting manufacturing and subtracting tests. and we need to transport the large-scale cell and assemble them. This is the technology at a very high commercial level. We are increasing our cooperation with domestic institutions and companies. We're cooperating more closely with local governments and businesses so that we can strengthen the basis for cooperation and demonstration of this technology. In summary, the nuclear heat from nuclear power plant is a carbon-free energy source which can be used for producing hydrogen and for various industrial processes. And we are now developing high-temperature gas-cooled reactor technology. Our 30 kilowatt level test facility is one of the most up-to-date SOC test facilities, which will be helpful for various industrial partners. And our actual test facility is at a commercial level. Its operational capability can be expanded to up to 2 megawatt level. So this will be very helpful for the technology development in hydrogen production. Thank you very much for your attention. Thank you for your presentation. Hydrogen production based on nuclear power. Through coupling between high temperature gas-cooled reactor and hydrogen production system, we can enjoy various technical benefits. Thank you.
Now we will invite Dr. Thomas O. Tree from the Pacific Northwest National Laboratory, PNNL, and the title is Enabling Reversible Hydrogen Storage and Transfer with Graphene-Based Carbon Boron Nitrogen Materials.
Thank you, and thank you for the invitation to join you tonight or this morning. Sorry, I apologize for the mouthful of a title here, but I really was excited about this opportunity to start to meet more people and talk about opportunities for collaboration. And so I really wanted to use this opportunity to share a new project that we actually just started a couple of months ago. So an outline, I just want to hit a little bit on the current collaborators and give a shout out and projects we're working on in hydrogen storage. So we're transitioning to hydrogen storage now. I want to give you a little bit of the inspiration for our fundamental studies that we're undertaking, give you some of the goals and vision we have for the fundamental research and specifically looking at things that could really enable long duration energy storage, things where batteries may not be able to provide the duration of discharge. I give you just a kind of an overview of our research approach to these fundamental studies. I don't want to go into the details too much, but because we're just getting started, but at least kind of provide you with what we think is critical, the questions we're trying to answer, and hopefully elicit some new collaborations, and just kind of close out with acknowledgements and some pointers for future collaborations. So some of our current collaborations now, we've been collaborating with Cheng Wan-Yun for a number of years now. Actually, when he got back to his graduate school days, when he was doing chemical hydrogen storage in the United States at Penn with Larry Smith. And so we've kept in contact and do and meet often at meetings and share our common interests. And then Hyung Soo, she's at KIST currently, and we are talking with her on a monthly basis to talk about catalysis studies, specifically for liquid organic hydrogen carriers. Our group is involved with a couple of different hydrogen storage projects. We've been involved for the last, I guess, since 2015 as part of a national lab consortium on looking at materials for hydrogen storage. And what I want to talk about today is this brand new project that we have funded. And I'll get into some of the details in the next slide or two. So first, kind of the inspiration, the Basic Energy Science Office of Science, Department of Energy, had a workshop. Chris touched a little bit upon this. I think some of the people from NL participated in this. I was able to participate in the hydrogen storage panel. And what came from this was a kind of an overview of the three areas of what is needed in fundamental studies for production of hydrogen, for storage of hydrogen, and for utilization of hydrogen. And I just want to, I guess, kind of call out, it's a mouthful here, but what I want to just kind of talk about our focus here is that really what, fundamental studies are needed to really be able to understand how hydrogen interacts with molecules and materials, and how can we tune those interactions. It turns out there's been a lot of research in hydrogen storage. The hydrogen is either bound too weakly or too strongly. And so if there's some way that we can tune that hydrogen interactions, that would make these storage reactions much more efficient. And so that's kind of the focus of what we're going on. So our key question that was proposed by the Department of Energy Office of Sciences specifically for hydrogen storage, how do we control and tune selective interactions of hydrogen with materials? And this relates also to membranes that you have in the fuel cells as well as electrolyzers. There's all these hydrogen interactions, the interfaces. And so I guess my real big outlook is that understanding, any tools and methods we are developing to look at hydrogen interactions at these interfaces could have benefits that we haven't even thought about in other areas besides storage and the PIM fuel cells as well as electrolyzers. So the goals of this project, I apologize for this huge mouthful here, is we have this nice little cartoon picture here where we have these carbon graphene layered materials, and we're doping with nitrogen and boron. And so this kind of just shows, an interaction that we have hydrogen coming down, interacting with the surface, activating the hydrogen, making hydrides or protons or hydrogen atoms, and then watching them diffuse around. And so this is just kind of this very high level cartoon of what we want to understand is how hydrogen interacts with these sorts of materials. And initial studies we're not looking at metals, and we're taking this one step at a time. We're looking at nitrogen doped carbons is where we started for the last couple of months. We want to go to boron doped carbons and eventually go to boron and nitrogen doped carbons, because we think there's going to be some really unique chemistry that can occur. So as I said, our vision is for hydrogen storage. It can really make and there was talked about earlier about the versatility of hydrogen, right? It can be a chemical reductant. It can be used to generate energy. But where we see this at is we align with the Department of Energy over the last year and a half. Have come up with these Earth shots. And what the hydrogen shot is really focused on making this hydrogen, as Chris so nicely described, for $1 per kilogram in the next decade. And we suggest that if we're going to, Dr. Yang mentioned that Korea is going to need 28 million tons of hydrogen on, I believe, an annual basis. How are you going to move and transport that hydrogen? And compression isn't probably going to do the trick. Liquefaction has some great advantages, but for long duration, boil off, there's lots of things. And so we are interested in storing hydrogen in chemical bonds and making this reversibly. So sort of just this, again, another high level cartoon is, we get the green renewable hydrogen from renewable electricity. It can be activated on the surface, and what Chang will talk about next are these liquid organic hydrogen carriers. And so you need catalysts to take hydrogen off and put hydrogen on. It turns out there are reports that suggest you can do this with these two-dimensional materials that are doped with nitrogen. And we proposed it could even be done with boron. But the idea is you can make a liquid hydrogen that's stable at room temperature, doesn't have to be stored at low temperatures or high pressures. It can be moved around in current infrastructure. And so we try and align our long-term goals with these two DOE Earthshots. So I just want to kind of touch upon how we've decided that we're going to approach this fundamental science problem. We have 3 different tasks that we're looking for collaborations in, that we're going to look at activation of hydrogen, and then the transport of the hydrogen as you get it activated, so you can get physisorption of hydrogen, then it can break into hydrogen atoms or hydrides or protons, depending on what you have on the surface. You can have the hydrogen move around on this surface and then be transferred to an oxidized heterocyclic arene, in this case, we just have a cartoon of pyridine, but there's lots of nitrogen substituted heterocyclics that people are looking at. You can reduce this and you can store it or you can move it. And then we want to be able to run this backward again and come back and go this way. So if we can understand any one of these steps, we think we're going to be making great progress in fundamental studies, but also if we can bring these together, it really can open up some new opportunities to store and transport hydrogen. So this is a really wordy slide. I just want to say that, for this, what we're trying to do with these active centers, we're starting out by taking graphene. So this is a combination of using people with expertise in chemistry, material science, computational theory, and experiment spectroscopy, and high surface area studies. We've started out by looking at, okay, we're going to make these 2D layered materials that are graphene, and we're going to start with nitrogen doping. And so we wanted to know where the nitrogen would end up. So we can look at the stability of the different materials. We can predict where the nitrogen will end up. We plan on doing NMR studies to try and benchmark some of these calculations. But then we'll be able to understand, okay, next, when we bring hydrogen down, what happens to this? So we're starting in this phase space of where we're just looking at nitrogen, somewhere along this carbon nitrogen here, but we're going to be able to move in all these different directions as we learn more about what we're doing. In the next phase of this, where we're looking at kind of this hydrogen diffusion, what's going on surface, we really think that we can modify the binding strength. And this is really critical, is being able to tune in this bonding strength of hydrogen. So it's, again, not too strong, not too weak. And if we have nitrogen and boron in there, we can look at things that are protic, and it was nicely talked about earlier about the Grotius method of having hydrogen transferred by water. There's similar mechanisms, but different with nitrogen that can move protons around. And then boron and hydrides, and how hydrogens can be transferred around here. But we're working with looking at supported surface, so that you will be doing some STM and XPS studies. And so this is Zdenek leads this task. And this was a paper that they published where he had this graphene on ruthenium surface. And it's maybe hard to see, but there are these black dots that are on here, and those are oxygen atoms. So he can look at oxygen atoms on this surface, and he does this at low temperatures, and then he heats it up. And if I don't have a technology breakdown, you'll be able to see as he heats this up, these black dots start to move around on the surface. And so we can start to model, and what the idea is, we want to do this with hydrogen now. And so we'll be doing this with hydrogen. So we've got this nice technique that allows us to look at the fusion of atoms on these surfaces. And then in the third part of our thing with this hydrogen activation, where we want to transfer hydrogen to organic molecules, either to take the hydrogen off or put it on to load it into this liquid phase. So we're curious about gas, solid, liquid interfaces and hydrogen interactions, right? So we really, the thing I'm excited about, and going back to what Chang was doing in graduate school, is looking at nitrogen and boron to activate hydrogen. And if we do this with carbon, we can tune these thermodynamics. And so we just started out, we're looking at how the surface might be, you might have some curvature in the surface or defects, and where the nitrogen. So this is using ab initio molecular dynamics and quantum chemical molecular mechanics, another group of theorists. So we have, what's really fun about this project, we have theorists that come from a molecular side of doing chemistry to theorists that are more in tune with doing materials type of calculations, as well as material synthesis and chemical synthesis. So I just want to kind of close out, like I said, I'm excited about this. This is a brand new project that's just started out. This is a team that's working on this. There's a little bit of overlap with our basic energy. With our EERE project that's more applied oriented, but this is really bringing in some new people into this area with expertise in these different areas. And then I just want to close out again with sort of like future areas of collaboration. So I mentioned these different hypotheses that we have. And so any kind of help in designing experiments or doing calculations to understand those, I think, is a starting point. But science, you start with a hypothesis, you test it, and you go make a new hypothesis. So that's, this is our starting point. And so this is what we would like to do through future collaborations. And I just have this cartoon here, right, is that we developed, we started thinking about hydrogen storage. You either have to cool things way down to low temperatures to have them stick to high surface area carbons or molecular organic frameworks, or you have chemisorption and you have these strong carbon hydrogen bonds or nitrogen hydrogen bonds. And so you need a catalyst, you have to put in a lot of energy. If you put in a lot of energy and heat, where does that come from? That reduces your whole overall efficiency. So if we want to go from power to gas to power, we want to be able to optimize all of those steps. And so we're looking at, how do we get into this mesosorption area? And what I'm excited about personally is that I think that there's some similarities and some differences when we look at connectivity of carbon-borne and nitrogen and molecules. And so we've been doing that for a long time, almost 20 years. But now we're doing this in materials. And so if we can sort of start to look at similarities and differences between molecules and materials, then we are going to be able to actually hopefully tune this and come up with ways to predict how to tune molecules. And so this is my final slide. And I want to thank you for having this opportunity and look forward to further discussion.
Thank you for your presentation, Dr. Autry from PNNL. So Dr. Autry has explained to us about the reversible hydrogen storage and transfer with the graphene-based materials.
Next, I would like to invite the last speaker for the session. I would like to invite Professor Yoon Chang-won from Postdoc. He's going to make a presentation on this topic. And due to some urgent circumstance, Professor actually sent us a pre-recorded video. Please understand this.
Good afternoon, everyone. It's my great pleasure to be here. I'm Chang-won Yoon from the Department of Chemical Engineering at Pohang University of Science and Technology, Postdoc. Today, I'm going to talk about liquid chemical hydrides as high-capacity and long-distance hydrogen carriers. First, let me open my presentation slide. Okay, here we go. Before my presentation, I'd like to tell you that a part of the work here has been done when I was at KIST, Korea Institute of Science and Technology, in collaboration with Dr. Hyung-Soo Jung. Okay, first let me talk about our national policy for hydrogen. The Ministry of Trade, Industry and Energy announced the Hydrogen Economy Implementation Basic Plan last year. According to the Basic Plan, hydrogen demand will be 3.9 million tons by 2030. This number will increase significantly to approximately 28 million tons by 2050. If you look at the number here, most of the hydrogen will be used for power generation and industrial section. Considering the economic feasibility and production volume of domestic CO2-free hydrogen production, the South Korea will need to import a large volume of CO2-free hydrogen from abroad in the future. The question is then how we import the significant quantities of clean hydrogen. As you may know, hydrogen has a 2 or 3 times higher gravimetric energy density than gasoline and diesel. However, considering the current fuel transportation, such as a very large crude oil carrier, which is called a VLCC, the very low volumetric energy storage density of gaseous hydrogen makes it difficult for different types of energy applications. Therefore, we need liquid hydrogen carriers for high capacity and long distance hydrogen transportation. The concept here is we can use L, which is a chemical, as a hydrogen storage medium. The L will react with clean hydrogen chemically to produce liquid chemical hydride. The liquid chemical hydride formed will be transported into a design site, which is called this hydrogen city, and the chemically stored hydrogen in the chemical will be extracted by chemical reaction. Finally, the produced hydrogen will be supplied into fuel cells and or hydrogen turbine to produce electricity. The liquid hydrogen carriers have a lot of advantages. For example, liquid chemical hydrides are typically stable liquid at ambient or near ambient conditions, which means is we can store significant amount of energy for a long time. Additionally, liquid chemical hydrides have high volumetric hydrogen storage density of over 45 kg per cubic meter. Most importantly, we can use existing infrastructure for storage and transportation, which means is economically viable hydrogen transportation is possible. Here is the more detail. At a hydrogen production site, we can use renewable energy to split water to produce green hydrogen, and or we can use fossil fuel such as natural gas. So we proceed the natural gas reforming process to produce blue hydrogen following CCUS. The produced CO2-free hydrogen will then be hydrogenated using a hydrogenation plant which is located at the hydrogen production site. The hydrogen-rich chemical hydride will be transported into a design site, and at the site, a dehydrogenation plant will extract hydrogen from the hydrogen-rich chemical hydride. Finally, hydrogen will be supplied into fuel cells and or a turbine to produce electricity. Postec and KIST together have been conducting relevant research on chemical hydrogen storage based on the concept I mentioned. We use small molecules as hydrogen storage media, and the rest of the concepts are identical. If you use nitrogen as a small molecule, then hydrogen energy carrier could be ammonia. If you use CO2 here as a small molecule, then hydrogen energy carrier could be methanol, methane, formic acid, or other LOHC, liquid organic hydrogen carrier. Now we are focusing on ammonia and formic acid and LOHC. So let me a little bit more talk about these chemical hydride. Okay, let me first talk about liquid organic hydrogen carrier. For the first time, we consider formic acid as a liquid chemical hydride. This is because the formic acid is non-toxic and a stable liquid at room temperature, and it has a high volumetric hydrogen storage density of 53 kg per cubic meter, which is higher than that with 700 bar compressed hydrogen storage system. And the formic acid dehydrogenation is relatively easy, so you can proceed dehydrogenation reaction even at ambient condition in the presence of an appropriate catalyst. But the catalyst development is very important because what we want to do is to activate CH and OH bonds to produce hydrogen, which is the desired reaction. But our catalyst can activate CH and Cl bonds to produce water and carbon monoxide, which is a side reaction. In the side reaction, the produced CO, carbon monoxide, can poison platinum catalyst in a polymer electrolyte membrane fuel cell. So it's very important to develop highly selective and active catalyst for formic acid dehydrogenation. To develop highly active and selective catalyst for formic acid dehydrogenation, we prepared different types of palladium-based catalysts by varying support. Specifically, we employed nitrogen-containing support such as carbon nitride, nitrogen-doped carbon, and amine-functionalized SPA15 species here. So what we found is that nitrogen functionalities in these catalysts play dual roles in facilitating formic acid dehydrogenation by transferring electron densities into palladium active site for CH bond activation, as well as by promoting formic acid deprotonation for OH bond activations. Then we also modify active site to prepare palladium-based bimetallic species such as palladium ion, palladium copper, and palladium nickel. Likewise, palladium alloying species plays an important role in accelerating formic acid dehydrogenation by modifying surface electronic structures via transferring electron densities for CH bond activation. In addition to the formic acid, we developed different types of liquid organic hydrogen carrier. We employed the biphenyl, which is a solid at room temperature. We also use diphenyl methane, which is a liquid at room temperature. When we mix these cyclic compounds together at room temperature, a eutectic mixture was formed. This is called a BPDM. And the BPDM can react with hydrogen in the presence of ruthenium aluminum catalyst at 150 degrees Celsius under 50 bar of hydrogen to produce perhydro-BPDM, which is hydrogen-rich form and liquid at room temperature. The produced perhydro-BPDM was successfully dehydrogenated, and based on this system, hydrogen storage capacities were calculated to be 6.98% by gravity and 60 kg per cubic meter by volume. So based on this system, reversible hydrogenation and dehydrogenation was possible. KIST then further developed relevant hydrogenation and dehydrogenation system utilizing BPDM as a LHC. As you can see the picture in the right side, a dehydrogenation system was employed for hydrogen extraction from perhydro-BPDM. The produced hydrogen was supplied into a PEMFC to generate 500 watt of power continuously without any problem. The developed LOHC was then tested for repeated hydrogen storage and hydrogen release reactions. And as you can see here, the BPDM can successfully hydrogenate it, and the produced perhydro-BPDM can successfully dehydrogenate it. So 9 times repeated reaction shows nearly unchanged hydrogen storage capacity, which means is the developed LOHC can be used for reversible hydrogen storage and hydrogen release. Based on the result here, KISS is now scaling up a LOHC dehydration system with the capacity of 5 kilogram hydrogen per day class. Okay, let me switch gear and further discuss about an inorganic hydrogen carrier, liquefied ammonia. To achieve ammonia dehydrogenation, we developed several heterogeneous catalysts shown here. Most of them are based on ruthenium as an active metal, and we vary support here. And we employed lanthanum-doped alumina as a support. We also use zeolite and nitrogen-doped carbon and silica as supports. Additionally, we also developed nickel-aluminum alloy catalyst for ammonia decomposition. In the case of the first catalyst, ruthenium supported on lanthanum-doped alumina, we conducted a technology transfer to US and Korean company. Let me a little bit more talk about this. When we tested the activity of ruthenium supported on lanthanum-doped alumina for ammonia decomposition, it was found that ammonia conversion is highly sensitive to lanthanum content. As you can see the left graph, when 20% more of lanthanum was doped in the support, nearly 100% of ammonia conversion was observed at 500 degrees Celsius. The catalyst also shows an excellent durability. The graph in the right side shows you highly stable characteristics of the catalyst. That is, the ruthenium catalyst shows about 99.8% of ammonia conversion for 6,900 hours without decomposition. The TEM studies indicate that small-sized ruthenium nanoparticles are formed. Let me continue to introduce one of our recent results on ammonia dehydrogenation catalyst. Catalytic ammonia decomposition is a structure-sensitive reaction. It has been suggested that ruthenium B5 type surface site, which is a step on the 001 surface of hexagonal close-packed ruthenium, is an efficient site for ammonia dehydrogenation. Our idea is to use two-dimensional hexagonal boron nitride with a dominant 001 facet as a template, so we may generate ruthenium B5 sites by epitaxial growth. Based on the hypothesis, we use hexagonal boron nitride as a template and conduct ruthenium impregnation using ruthenium carbonyl species as a precursor. After calcination, as you can see here, nano-sized hexagonal close-packed ruthenium nanoparticles are uniformly prepared on the hexagonal boron nitride surface. Morphological study shows the formation of elongated hexagonal-shaped ruthenium nanoparticle with round edges. When we analyze the box area of the picture, B5 type step is formed. Additional cross-sectional hard STEM studies again indicate the formation of ruthenium B5 site. Based on the result, we further model using the elongated hexagonal-shaped ruthenium and found that B5 sites are formed along 001 and 101 edges, which is consistent with the experimental observation. We find that the more planar the shape, the sharper the corner of the hexagonal ruthenium nanoparticle, the higher the density of the B5 sites. Then we test the prepared ruthenium boron nitride catalyst for ammonia decomposition at 450 degrees Celsius. GHS3 is shown here. For comparison, we also employ ruthenium alumina and ruthenium silica catalyst for the desired reaction. As you can see here, ruthenium boron nitride shows higher activity than other two catalysts. The ruthenium alumina and ruthenium silica catalysts decrease their activity with time. We then analyzed the used catalyst by TEM and found that the ruthenium size of ruthenium boron nitride is not changed significantly, while those of ruthenium alumina and ruthenium silica increase significantly. One notable thing in the graph is that the activity of ruthenium boron nitride increases at the beginning of the reaction. So we further monitor the morphological changes of the catalyst in the presence of ammonia using in situ TEM. As you can see in the picture, hexagons with rounded corners become faceted hexagons with sharpened corners, indicating increased B5 site density. Finally, the activated ruthenium BN catalyst shows highest mass and specific activities compared to the previous reported catalyst. In addition to the catalyst development, system development is also in progress. KIST developed ammonia dehydrogenation system with a capacity of 5 normal cubic meter per hour. A 12-faceted and compact reactor was designed, and our developed catalyst was employed. As you can see here, the ammonia dehydrogenation system produced hydrogen, which was supplied directly into a PMFC, generating the power of 5 kilowatt continuously. Based on the result, the total system efficiency was calculated to be about 84%. Now, the POSTEC, RIST, KIST, POSCO consortium is now developing a highly efficient ammonia dehydrogenation demo plant with a capacity of thousands normal cubic meter per hour. Finally, I'd like to mention that we do research collaborations with U.S. national laboratories, although Korean U.S. institutions are not connected by research projects. KIST PNNL has been collaborating each other on liquid hydrogen carriers. Furthermore, POSTEC LIST will conduct a project associated with life cycle analysis of blue hydrogen pathways in collaboration with Argonne National Laboratory. Additionally, KIST LLNL is now discussing about potential collaboration on hydrogen production and storage. Thank you very much for your attention. If you have any questions, please contact me or Dr. Hyung-Soo Jung at KIST. Thank you.
네, 윤창원 교수님 발표 감사드립니다.
Thank you very much for your presentation. We have listened to all presentations for session 2. Next, we're going to begin the last session, which is panel discussion. I would like to invite the moderator. The moderator of the panel session is Mr. Jang Jong-hyun from KIST. And panelists, Professor Kim Chang-hee from Cantech and Mr. Kim Jae-kyung from Korea Energy Economy Research Institute. I would like to ask the moderator to proceed with panel discussion. Good afternoon, ladies and gentlemen. I am Jang Jong-hyun from KIST. From early in the morning, we talked about hydrogen-related policy strategies and technology R&D status. We're going to spend about 30 minutes for a panel discussion. We will talk more about the Korea-US cooperation in hydrogen technologies. And Professor Kim Chang-il and Dr. Kim Jae-kyung are here with us as panelists. First of all, let's talk about our perspective on global hydrogen economy under global hydrogen economy, how Korea and the US could cooperate with each other. This is the main topic of the discussion session. Dr. Kim Jae-kyung, could you make your comments first? Good afternoon, ladies and gentlemen. I am from Korea Energy Economy Institute. I am going to talk about the market first of all. In terms of energy market and hydrogen economy, the Ukraine war is a very important turning point. After the Ukraine war, our world has transitioned to a very much different world. And there was another important event. In August this year, Canada and Germany signed an agreement to trade hydrogen and Canada decided to supply hydrogen to Germany. Due to the Ukrainian war, Germany is going through energy crisis because it is not it's not receiving sufficient amount of clean energy, and Canada will supply hydrogen to Germany according to the MOU. So far, in the global hydrogen economy, carbon neutrality and environmental policies were the very basis of the global hydrogen economy. But now hydrogen is being handled as an important element of energy security. These days, in terms of energy security, we are going through a lot of discussions on how we could approach hydrogen. And in this area, Korea and the US are the very important allies to each other. And for Korea, the US is one of the most important trade partners. And for Korea, the US is also a very important market, especially it's an important market for consumables and in terms of technology development. Like in order to develop our water electrolysis or pyrolysis technologies, and in order to export vehicles to the US, we cannot ignore the importance of the US as an important market. And due to the Inflation Reduction Act in the US, we could see more opportunities to make our way to the US market. And in the case of the US, we could become a good partner to each other in terms of the import and supply of hydrogen. And in 10 years from now on, the US will be able to produce hydrogen at the cost of $1. So we could find very good opportunities for cooperation between the two countries. Thank you very much for the very good comments. So from macroeconomic perspective, there are various situations taking place, and considering the global hydrogen economy context, is there anyone who would like to give their opinion about the Korea-US cooperation? So it could be like a national strategy, or it could be about any potential R&D ability or potential. Professor Chang, do you have any comments regarding the cooperation potential between the US and Korea? I think your microphone is off. Yes, between the Korea-US relations, well, the hydrogen economy in that regard is not my expertise, but I believe that businesses are already Korean companies are already entering the US market to start their business there. I have met some people who are doing that already. And at the government level, I believe that there should be supports provided to facilitate that kind of business level
cooperation, there should be a lot of laws and regulations or incentives created to facilitate that. And in the US, there are tax breaks for EVs, only for EVs manufactured in the US. And that reflects the position of the US government, what it's going to pursue in the future. And it is not limited to just finished cars like EV, but whether it will also be applied to the hydrogen supply chain in the future. So we have to find a way to understand the future direction of the US government.
Thank you very much for your comments. And I would like to ask Professor Yoon Chang-won from Postec. He actually made the last presentation. During the presentation, he mentioned that he is cooperating with the U.S. institutions in terms of R&D. Then, in terms of R&D, how do you think Korea and the U.S. can cooperate with each other? Yes, nice to meet you. I am Yoon Chang-won from Postec. I gave you the pre-recorded presentation video. Korea and the U.S. research institutions have cooperated with each other in the R&D activities, especially on hydrogen storage. We have closely cooperated with each other. In the case of KIST, PNLL, Dr. Tom Autry has been closely cooperating with KIST, and Postec and LIST have been working with another U.S. institution on blue hydrogen production and transportation as well as storage. They are analyzing this aspect. In the case of KIST, with Lawrence Liberational Network, we conducted joint workshops 2 times to discuss how to discover and develop our joint research projects. Now, in the case of the US and Korea, hydrogen production, especially green hydrogen production, and large-scale hydrogen storage, and long-range transportation, and liquid hydrogen carriers, and many other technology elements exist that they actually require our cooperation. But for now, we don't have enough joint research projects going on between the two countries. In the case of hydrogen, hydrogen technology development cannot be done with just effort of only one country alone, but we need to form cooperation or cooperative network among different governments, academic sector, and research institutions. And if we establish a cooperative network among government, research institutions, and academic sector, then it will be helpful in the future.
Thank you very much. From PNNL, we have Dr. Autry. He asked some questions. He made a great presentation about the hydrogen storage. And I want to ask some questions. There are some questions to Dr. Autry from presenters. They have wrote it on their Zoom chatting. So can we ask the question here? Or should Dr. Autry write into the Zoom chatting?
I know I wrote a bunch of questions, but I didn't know if anybody wrote questions to me. So
아니요. 오트리 박사님께서
So actually, I can see that Dr. Autry, you have asked questions to other presenters. So to Professor Chang Seung-soon, you asked that in slide 9, there is this slide about PEM membrane, and there is H2 in and H2 out. And the question is, how much H2 goes through the membrane and how much is not transported, and whether you are considering the possibility of recycling. Can you answer it, Professor Chang?
Dr. Autry, I already wrote my response and my answer to the chatting room to the moderator. But I'm glad to mention that again here. So first of all, in our simulation, so as you used in your own presentations, there is a DFT study and also MD simulation studies for fuel cell membrane system. And then in our simulation condition, frankly speaking, we do not consider such hydrogen bypassing or crossover, and also even oxygen crossover was not considered. But I believe it is very important point. So in my written answer to the moderator was that we will gladly consider that aspect of it is really important point. So as you know, for example, Nafion membrane methanol crossover was significantly studied for methanol fuel cell system. Because of that, many hydrocarbon based membranes has been studied well. So now it is a time to think about H2 bypass and also O2 crossover for our membranes, starting from Nafion to other promising hydrocarbon systems too. So that's what I can say right now.
And can I follow up? I mean, that was beautiful,
Sure.
beautiful, elegant work. I had even a more simplistic question when I think about what Chang presented with formic acid. He's making hydrogen and carbon dioxide at the same time. And carbon dioxide, I don't think, is a poison for fuel cells. And so when I saw this beautiful scheme you had, the hydrogen goes by, some of it goes into the fuel cell, some of it goes out. Could you take in a mixture of 50% hydrogen and 50% CO2 and just have the CO2 come out with some hydrogen and some of the other hydrogen go in? And there's probably CO2 crossover issues.
Oh, I see. Dr. Autry, so if you don't mind, probably my understanding is that you are thinking of the CO2 reduction reactions, also, is it right?
Well, I'm trying to hope that CO2 doesn't do anything, that your fuel cell, that I can throw a mixture of hydrogen and CO2 at a fuel cell and have it provide electricity. And the CO2s, I know carbon monoxide would be a poison, but CO2, I don't think it shouldn't really react. You might get water gas shift at higher temperatures, but it would be really nice if there was a fuel cell that you could take mixtures of hydrogen and CO2, because most of the time you talk to fuel cell people, you need 5 nines hydrogen for it to operate. That can be hard to come by sometimes. Are there fuel cells where you can actually have mixtures of gases that go in, and the efficiency will drop, but it would make it a lot easier than if we had to do a separation step or pressure swing absorbance to come up with 5 nines hydrogen.
I see. So I believe it is also a very good point. And then, so we will also think about such mixed gas system. But right now at the moment, we are developing the catalyst system for CO2 reduction in the presence of hydrogen. So many times hydrogen H2 evolution and also CO2 reductions are competing reactions. And then, how can we improve the selectivity of the catalyst system? So that is another but very important topic. So probably my answer is not really the answer you are looking for, but what I can say is that at the moment I separate those two issues in my lab and then pursue those separately, but mix this gas system for the feed into the fuel cell, like H2 and O2 crossover. Thank you very much. We will look at that. We will take a look at that.
I'll follow up because I mean, I still, I think it would be great to collaborate with somebody who could give me a fuel cell where the CO2 just comes out and I don't want it to do anything and the hydrogen goes in.
I see. I see.
With
I
the
see.
formic acid.
예, 예.
Mhm.
I'll follow up later.
오늘
Alright.
그 이런 자리를 기회로 해서 앞으로도
Yes,
더
on the
우리가
occasion
지금
of today's forum,
자료들을
you'll be able to
기대하겠습니다.
further develop your
넬
discussion.
하이드로젠의
And
카푸아노 디렉터님에게도
from
질문을
Nail
주신 것이
Hydrogen,
있었는데요. 첫
the
번째
Capuano
질문은
director
1기가와트
received the
하이드로전을
question.
가지고 수소를
With
시간당이라든지
1 gigawatt
얼마나 많이 생산할 수
PEM
있느냐라는
hydrogen,
질문을
how much
첫 번째로
H2 can
드렸고요.
be produced
두
per
번째로는
hour?
9마일
And
뉴클리어 플랜에서
in the
펜을
9
어떤
Mile
식으로
nuclear
이용하는지
plant,
두 가지 질문을 주셨습니다. 여기 대해서
how is
답변
PEM being
부탁드리겠습니다.
used?
So the 1 gigawatt system, I don't know the precise number, but I know it's over 500 tons per day. So you can calculate how much that is per hour, I guess. It's actually closer to 600, I think, maybe 575 tons a day or so, for a 1 gigawatt system, and that applies to both PEM and alkaline. A gigawatt of power in is kind of the same in both. So the nuclear installation, I'm not entirely sure what 9 Mile Island is using it for, but I do know that, and this is probably the case for this installation. Nuclear power plants like to run at 100% capacity all the time, or near that. They like to run steady state. But the demand for the electricity that it generates is not always at peak need. And so I think that these installations are looking to use the electricity that's not in demand, plus the heat that's generated from the process, to feed into both low temperature and high temperature electrolysis systems. So the heat generated from the nuclear reactor could be used for the high temperature solid oxide electrolyzer case. The extra electricity that's not needed would then be used to generate hydrogen that can be stored for many different applications. It can either run back through a fuel cell to provide peak power in the instances where the demand is higher than the capacity of the plant. You could run that back through a fuel cell and collect the electricity to augment the nuclear energy, or during the low so anyway, to essentially provide peaker power for all this. But also, if you have the gas stored, it doesn't necessarily need to go back into a fuel cell. You can use it for a lot of different other applications. You can use it as green hydrogen, near green hydrogen into an ammonia synthesis process, or really anything that needs a reducing environment of very high purity hydrogen.
예, 말씀 감사드립니다.
Thank you for your comments. Next discussion topic is the all life cycle. The technology for all life cycle of hydrogen is very important. And in Korea, we are discussing how we could receive the supply of green hydrogen, how we can produce and use green hydrogen. This is an important issue. And if you look at the Korean policy for renewable energy, we cannot exclude green hydrogen.
의견 말씀을 부탁드리고자
I'd like to ask you to make your comments, and could you share your idea with us, Professor Kim Chang-hee?
반갑습니다. 한국에너지공대 김창입니다.
Nice to meet you. I'm Kim Chang-hee from Kentech. So regarding the green hydrogen, well, there are government policies, and we have the government's plans to connect that to the power grid, the renewable power grid. There are various energy basic plans and carbon neutrality scenarios established by the government by 2050. About 200 to 300 gigawatts of renewable energy will be supplied. And if you look at the entire energy grid of Korea, unlike Europe or other countries, we are very isolated. To the north, we have North Korea, and we are surrounded by oceans on three sides. So we are like an island in some sense. And because of that, there are some tasks for the renewable energy as well. In Korea, the areas that will have the most renewable energy distributed or supplied would be Jeonnam and Jeonbuk province. If we supply over 200 gigawatts, about 70 gigawatt will go to Jeonnam and Jeonbuk. And that is almost the same as the current power supply size. In Seoul, from Seoul, actually, we have a lot of power facilities that are supplying power to Seoul, located in Jeonnam, and also for the nuclear power plants, we have them located at the coastal areas of Korea. And because of that long distance from the production facility to the demand site, we have a lot of transportation cost. Jeonbuk, Jeonnam areas, if they receive most of the renewable energy facilities, then it means that eventually the green hydrogen production sites will also be biased in those a few number of locations, and then it will entail the storage issue and transportation issue. And there was a question that regarding like the hydrogen supply by 2050 to be purely clean hydrogen. And to achieve that, we have to have a lot of research on electrolysis. Neil said that in 2009 that you have started the research on connecting the grid to those hydrogen. Most of European companies have or are carrying out those researches. In Korea, since 2015, we have started this study. So it's not like the general hydro electrolysis, but mostly focused on how to connect this to the renewable energy. So I think that in this regard, there are some possibilities to cooperate with other countries.
좋은 말씀, 좋은
Thank you
말씀
very much for
감사드립니다.
the good answer.
지금 수소 생산 전력으로
As the
재생에너지
source for
전력 공급을
hydrogen
많이
production,
들어가고
renewable
있는데
energy and nuclear
그런
power are
포함돼서
being considered as
이재명
viable
관련주가
candidates. Dr. Kim
부탁드리고요.
Jae-kyung, could
이런
you
원자력
share
원천을
your
필요하다고
idea on this?
보시고
And Dr.
의견
Park
말씀
Byung-ha,
부탁드리도록
could you
하겠습니다.
also share your opinion on this topic? Thank you. Due to time constraint, I'm going to immediately talk about my opinion. In May this year, Korea had launched a new administration. The hydrogen economy plan has been implemented from the previous administration, and the Yoon Suk-yeol administration has also implemented the hydrogen economy plan. And fortunately, I don't think the new administration is going to change the existing hydrogen economy plan. And as Dr. Kim Chang-hee mentioned, the biggest issue in Korea is that we need a lot of renewable energy for producing green hydrogen. And the Yoon Suk-yeol administration has totally different stance on renewable energy compared to the previous administration. In hydrogen economy, renewable energy is very important. The amount of supply of renewable energy is very important. From the Moon Jae-in administration, renewable energy, especially solar power and wind power, have been considered, but most of the renewable energy in Korea was provided through solar power. Solar power accounts for 90% and wind power accounts for 10% in Korea, and that brought about side effects. For example, due to geographical characteristics, in Korea, we don't have much site for establishing large-scale wind power plants. And in the case of solar power, they have a high level of power generation unit cost. And so the policy direction is now being changed in a way to strike balance between solar power and wind power, maybe 6 versus 4 between solar power and wind power. But in the inland area, we don't have much site for the wind power infrastructure construction, and so the supply of renewable energy is a very important issue in Korea. We will have to look at some sites in the marine site so that we could use marine wind power plants. But marine wind power, water electrolysis, and hydrogen, how these three elements can be connected to each other, we need to create a model. Korea Oil Corporation reviewed this idea before, but for now, we don't have a clear model that will connect the hydrogen technology with marine wind power, offshore wind power. So I think for this, we need to cooperate with the US. Secondly, the Yoon Suk-yeol administration puts great importance on nuclear power, which is different from the previous administration. The previous administration was focusing on phasing out from the nuclear power. However, the new administration is different. The new administration is trying to make more use of nuclear power. And when we think about hydrogen production, through coupling of hydrogen production system and nuclear power system, we should think about the balance of the regional balance rather than transportation or production. We need to think about the transportation of hydrogen, especially large steelmaking companies have higher demand to hydrogen. For example, steelmaking companies' demand for hydrogen could be similar to the entire hydrogen demand of Korea. Then do we need to import hydrogen 100% from other countries? Then if we import hydrogen 100%, that could not ensure stable supply of hydrogen. So we need to think about coupling hydrogen production with nuclear power reactor related systems. And in order to meet the demand for hydrogen from steel making companies in Korea, we need to think about the technologies that will enable us to secure stable supply of hydrogen. And we need to think about the continuity of policies among different administrations because the previous administration and the new administration have opposite stance on the nuclear power policy. So when the current new administration is changed in the future, then we should ensure consistent policy implementation. Also, we need to think about long-term stability and consistency in the policies. And regarding nuclear power system, we should think about how we could properly deal with the highly radioactive spent nuclear fuel, for example.
Thank you for your great comment. We will hear from a researcher Park Byung-ha from Korea Atomic Research Institute.
Thank you. If we use nuclear power as the source for hydrogen production, nuclear power has advantages because nuclear power plants are available 24/7. Whatever the hydrogen facility, whether it be HTSE facility, the capacity operation rate is over 80%. So nuclear power gives you much more advantages than renewable energies as the source of hydrogen production. A nuclear power plant has such a large scale, so we can ensure large amount of hydrogen production. And refueling cycle is relatively longer. So in terms of energy security, nuclear power can make a great contribution to the hydrogen supply. And We need to supply hydrogen to the region that has a high demand for hydrogen. This is why we need to think about the geographical elements. The hydrogen transportation cost is very high, and we are very well aware of this issue. As of now, we have to put 3 to 5 kilometer distance between nuclear power plants and any other facilities due to safety. And we conducted various studies on safety, and we are trying to reduce the distance limit between nuclear power plants and the facilities that demand hydrogen. So if we work on this and if we successfully work on this, we will be able to supply hydrogen to the user of hydrogen from a shorter distance. Nuclear power technologies are already mature. They are enough to help produce hydrogen. And once we get consensus from the people, nuclear power can make a great contribution.
원자력 연계된 수소 기술에 대해서 좋은 말씀 주셔서
Thank you
감사드립니다.
for your comment on the hydrogen transportation connected with the atomic power. Thank you for your great comments and presentations. So we could hear that hydrogen is not just about energy, but it has to do with environment, industry, and national security as well. I believe that everybody understands that point, and that's why we are so much focused on hydrogen. And in that regard, the cooperation between Korea and the US should be the core strategy. And taking today's forum as a momentum, I hope that there could be a lot of practical and constructive cooperations between the two countries. And I hope that all the participants here will put their utmost efforts to make that possible. I want to thank all the presenters and panelists and all the other staff who made today's forum possible. Thank you very much.